So just for everybody here, we're being recorded on Zoom, and the presentations will be made available later on both the YouTube channel called VMCAI 2021. Just for everybody here, we're being recorded on Zoom, and as you can hear, it's working. Made available. And it'll also be recorded by Zoom, so we'll make the individual presentations available for seeing them later. Watching them later. It is 4 p.m. here where I'm sitting, which is in Copenhagen. So this is Central European time. Welcome to the third day of VMCAI 2021. So we'll get going with another invited talk. In fact, we have two invited speakers, Bernhard Steffen and Dave Schmidt. And it's my great honor, actually, to introduce the two of them. They've made a lot of impact on my perception of computer science and my interest. And some of the work that brings them together is actually model checking and data flow analysis. And to quote a very, very well-known person in our community, he said at some point, this is the work that got him into the field. Okay, so this has been absolutely fundamental, you could say. Now, Bernhard will be giving the invited talk, and it's based on a paper that is published. You can see it together with a co-author. Dave has been so kind to actually be around then at the end and and lead the discussion after Bernhard's invited presentation. So just briefly, Bernhard is an absolutely prolific person. So I think everybody here in this community knows him. He's already been chair 3 times at VMCAI. He's done absolutely enormous amounts of work. I mean, his production is just astounding, with more than 300 papers. I think it's 350 papers. And he's both covering wide in terms of the topics. So if you look at it, you will be surprised. You will know a lot of his work, but actually not by far all the other thing that he's doing. And it's also deep. So it's ranging from fundamental core computer science with his background in mathematics and computer science to absolute applied applications in industry. Has had his own company, a successful company for a number of years. He's the co-author of major tools for the area, JABC, and especially what's probably best known here is the concurrency workbench. He's in general worked with software engineering and formal methods. Just to highlight, he's a number of most important and most influential paper and artifact awards, and he's also the co-founder of the ISLA series of biannual conferences that I personally have experienced and very happy about. It's a unique combination of being able to talk to colleagues and having small workshops and tracks that go into the depths without the intensity of, you might say, the necessary of like 10 or 15-minute talks as we have here, unfortunately. He's been dean, he's done a number of things. He's been the force behind turning the University of Dortmund into the Technical University of Dortmund. He was at the age of 19, I don't know the age, sorry, Bernhard, 93, he was already full professor at the University of Passau after a number of positions he had at Edinburgh gosh, I'm sorry, Bernhard, I've known you a long time, but your resume is so long, I have to move on. So in fact, actually sitting next to him for a day and just watching him is so exhausting. You need a day off the day after work. So anyway, the other one is great colleague Dave, who I met at DICU and who's visited, luckily for us, DICU many times. He's an absolute phenomenal, I think, presenter and actually developer of technical material. His textbook on denotational semantics, I encourage you to look it up and pick it up, was the book I taught from the first time when I was at DICU in 1991. And he's done similar work also on abstract interpretation from denotational specifications. And recently we wrote a paper and I thought we had done something very clever until we realized Dave had done it in 1995 in natural semantics-based abstract interpretation. So Dave's been there, so watch out. The two of them actually, for me, stand for the complexities and the simplicity of the same time combination of model checking and data flow analysis. With that as a background, Bernhard is looking forward, of course. The word is yours, Bernhard. Thank you.
Yeah, thanks a lot. I should probably start sharing the screen. Oh, I'm not allowed to. Host disabled participant to share screen.
Yes, so there is something that gets set up every single time. But you know what? Try it again.
Let's do a second time. That's good. It should be where's my, here it is. Yeah, share, oops. I have to, wait a second. I have all this stuff in the. Wo kann ich, da. Wo kann ich das jetzt, The Zoom is in the way that wait a second, I have to go to lower, wait a second, I have to go to full screen, but the Zoom controls are on the way. Now I can do it. So, okay. I'm on the wrong thing. So this is what you will see, very fast backwards. Now let's go forward. So thank you very much for the very enthusiastic introduction. In fact, Dave and me, and Dave will say something at the end, connects this data flow as model checking idea, which I had in 1990. So this was when I came to Edinburgh because I did data flow analysis as a PhD student, and then I moved to Edinburgh where I worked on model checking. Anyway, for me, this connection was in fact not so much an algorithmic one, but a completely different one by looking at it or feeling it as a kind of flavor of a domain-specific language, as we would tell it today. So for me, the change was not so much that I save space or that I can generate efficient algorithms or that there is a connection, but that viewing static analysis from the perspective of temporal logics is a kind of mind changer, because you suddenly move from a kind of how perspective, how to compute stuff, to a what perspective of what you want to compute. And I hope that my slides will kind of give you an impression of what I thought at that time. And in order to not speak about stuff which is 30 years old, I introduce a few other things. And I'm very happy that I saw Elko Visser here, because he is certainly one of the big experts in language workbenches and domain-specific languages. So some of what I'm explaining is probably perhaps interesting for him also. Okay, so here's the domain-specific language in which I express the structure of my talk. So it's just these three bubbles. And in essence, we want to look at three, let's say, patterns of domain-specific languages. Everybody knows Backus-Nauer form. I think structured operational semantics is well known in the community. And the question mark for TL means that you may look for some temporal logic. In fact, in the talk, we will have both a linear and a branching temporal logic. And I will show and exemplify in my talk, these three language families, I would call them, and show what they or why they are good domain-specific languages for certain problems. So the first thing is, of course, I have to get rid of here because I can put it here. So the first thing is I want to start with structured operational semantics, but you can imagine whatever we do, I mean, there's a BNF sitting below it. We have a programming language, of course, syntax has been specified in BNF. So in a sense, we always have BNFs around, but this is not the main point here. What I want to later on talk about BNF is not just the normal way of defining languages, but to make it a tool for language refinement and language propagation. Anyway, but let's start with SOS. And there we have, in fact, 4 steps. So we look first at standard SOS very briefly. Then one thing which I found always surprising, I used it in courses since 1990 and was surprised that this was not known. It was like folklore, that if you that you can make very easily a control flow analysis from SOS. Then we look at the labeled variant and at the end at some abstraction. And all this shows you some variants of SOS. So how we use the SOS pattern to express what we want to do. So of course, we start in the beginning here, you see a bit of BNF. This is the language we look at as an example now. This is just a simple while language. I don't think that I should go into detail here. And then we end up with SOS. So here is the typical structure, the structural operational semantics, the Plotkin style semantics of such a while language. Of course, you have the classical rule for assignments, the composition rule, which splits into, you can see my mouse, I hope, the composition rule splits into 2 parts. One for the terminating, here's for the terminating step in the first component, here for the one where the first component has to still continue. And of course, then we have this very elegant way of dealing with conditionals and while, here simply by splitting the rule and dealing with the condition just as a side condition. It's very, I think it's enormously elegant, and while is simply an unrolling. This is the normal pattern of SOS, and I think it's not necessary to go into it. Okay, the first step I wanted to show you, and which also really pushed me into this SOS pattern as a practical tool for many things, is to use it for control flow analysis. So what you can simply do is you collapse the states, the set of states, just to a single point domain, which is now here, the single point is this green square. And if you do that, of course, your expressive power is much reduced, but you get this set of rules. I mean, this is just a systematic transformation on the rule set. And of course, what you saw here, I mean, the conditions don't make sense any longer, because on that domain, it's impossible to evaluate Boolean expressions. So, and if you do that, okay, you can apply that to your while language. And now let's look at a very simple example here, which I didn't introduce yet. You can look at it. Okay, the full thing is up here. This is a factorial. Yeah, you compute the factorial for the initial value of x here. And this is then what you get. You get such a control flow graph. But when you look at it, you see this is not very nice. It's very redundant. So let's transform again, go back to our SOS and move from the one point domain as such to a labeled version. We just protocol or document the step we did. So you see that we just put the assignment up here, the skip here. We just document on each step what has happened, which elementary step. SOS is also saying it's a small step semantic. So which small step has been done is just recorded on the edge. And if you do that, you get again it's the same pattern. You get this funny language. And if you go back to our program, it looks like that. And now you recognize there's even more redundancy, but we can skip it. And we can just leave that away. And what we get is the control flow graph I like. It's much nicer than this classical control flow graphs for program analysis people, because it has the control, which we already evaluated in this SOS step. So you can see that as a partial evaluation of the program text. The control is evaluated. This is the sense of a control flow graph. And now we have these nodes free to put information. So this is what program analysis does. It wants to annotate the program with information. Okay, so let's go play with it. Let's just start, for example, with collecting semantics. I think collecting semantics, I think it was coined the term by Fleming Nielsen, is well known in the community as well. So let's look at a state here. Sigma 3 means the first component is the initial value of X, and the second index is the value of Y. And here we don't care because it's immediately overwritten. So let's start with any state where X has the value 3. And then now we can propagate that through. So this is just collecting semantics. You can just go and go. I think this is easy to follow. And now you have here a framework in which you can deal with collecting semantics. Of course, in general, you would do that for all initial states, and then you would collect the stuff up and would get information about which states are possible in which program location. Okay, this is one thing. Let's take something else. Symbolic execution, same thing. You can do this, play with it, go. Okay, whenever you have a back arc, you essentially collect the symbolic execution that's in OR here, and you can continue further and further, and this would be a kind of symbolic execution on that structure. Okay, this is something which we use quite a lot, with various abstractions put on top to get finite representations, and it's all just based on thinking of structured operational semantics as a main driving pattern. Okay, now let's come to the next thing, is abstraction. Okay, we take again, here a summary again of our factorial function, but let's just abstract here to what is the next step from a 1-point domain? Let's go to a 2-point domain, because we only look at okay, it's more than a 2-point because we have 2 variables. Yeah, so it's in fact a 4-point domain, and we compute on odd-even values. I think the odd-even interpretation of naturals is well known, or of integers. I have summarized here the functional tables, and now if you make, you compute SOS in a standard fashion, but you don't talk about concrete integers, but you just speak about the abstracted value to odd even, then you add up with this graph. And this funny thing about this graph is essentially telling the factorial is a simple example. Just for that, there is certainly stronger examples around, but it just should illustrate, just by executing the SOS and starting with values greater than 1, you can guarantee that the final state always has an even result. And you didn't prove anything. It's just executing the structured operational semantics. I think this is pretty much fun. And then there's something else which I wanted to show you. It's again can be seen as SOS. Also, back in the 90s, I developed something which is called property-oriented expansion. This is even kind of more abstract than, okay, it's very related to the odd-even example. There you compute on any kind of property. Okay, odd-evenness is kind of computing still on abstracted values, but here we compute on the domain of the power set of assignments, and we interpret such a set of assignments as all the assignments which are redundant at a certain spot. This is the idea. So it's a very abstract interpretation. So the let's say state component is only telling which computations are redundant. And okay, if we do that, we can tackle this program. Actually, I wrote my PhD about so-called partial redundancy elimination. And for people who try to eliminate redundancy, this is a kind of worst case program. I can make it as long as possible. There are lots of computations. There's a path with an arbitrarily high amount of redundancy, but you cannot eliminate anything because it's always necessary. There's always a path where that is required. And using now SOS or using the property-oriented expansion idea, or just, let's say, making analysis which executes not necessarily the syntax, but for example, the graph here on that domain, leads to this result. It tells you at each point which computations are redundant. You see, for example, that all these states here are the same. And if you do that, suddenly you get something which is a program which has no partial redundancies anymore. The fun thing is, this is what I showed. This was an invited talk for SAS in 1970, I think, in Aachen. That you can get rid of all partial redundancies. This was one.
Sorry, Bernhard.
It's only an abstract interpretation. Was that a problem?
Am I the only one having problems hearing?
No, no.
Bernhard, excuse me.
It's the same here.
Bernhard.
I think he can't hear us.
Okay. Bernhard, we cannot hear you. Bad sound.
Hello?
It's consistent with a bandwidth problem.
Hello?
So we unfortunately cannot hear you. I think he can hear. Anybody can't hear him, right? We unfortunately cannot hear you. Can you nod or do anything to indicate whether you can hear me? Can you hear me? Bernhard, can you hear me? It seems we have a bandwidth problem. And if you think about it, it's the first time during VMCAI we've had that. It's live talks. So that's the risk we're running.
I was about to say that we were fortunate enough.
Yes.
So this happens on the last day.
Yes. We'll get back on track. And let's just give Bernhard a little bit of a time to set it up, because he checked it before and assured me that he had turned off all the programs and things he is running. But when I asked him if he had turned off his Bitcoin miner, he was a little bit cagey. So,
considering the price.
Well, since this is being recorded, I did not ask him about the Bitcoin miner. It was a joke. Thank you. Okay, so. He'll come back. So maybe this is the. Yep. Sorry, David.
Yeah, Fritz, can you hear me?
Yes, we can hear you.
Great. Well, if it's the case that Bernhard is lost in the ether, I had about 10 minutes of remarks that could be inserted at any point. It doesn't have to wait till the end. It doesn't build on Bernhard's technical presentation.
May I
suggest that you go ahead and invite you to do that? We'll play it by ear, but please go ahead.
Well, that might make sense to do, since Bernhard's probably got a little bit of repair work to do on his end. And
Yes.
so I can just go ahead.
Please do.
When Bernhard contacted me about all this, I said, Bernhard, it's your job to do the technical bits. And so I wanted a few minutes at the end, but I can go in the middle or anytime, because what I'd like to do is first thank Fritz and the VMCAI people for getting us on the schedule. And also, it was nice to say hello to people like Andreas, who I've seen in this little box. And Tino Cortese, it's nice to see you again, even though it's from far away. And when I was thinking about what to say, I realized I've been doing this programming language theory stuff for about 40 years, which is a long time, and it makes me feel like an old timer. But it also made me realize that I've met a lot of other old timers. And the one who I want to talk about today is John Reynolds. And just for a few minutes about John. Maybe some of you remember John. Maybe you went to meetings with John. If you did, you know that he had one really sharp, deep intellect. And he made very insightful comments after talks. And sometimes they were very pointed and pithy, but you always learn something. And when I was reviewing Bernhard's materials that he's trying to present today, and I hope he'll be up to speed in a couple of minutes, I thought of two remarks I heard Reynolds make, which I think are relevant here to us. And the first one goes all the way back to 1980. It was a workshop in Aarhus. And it was a lot of talks on a funny subject called semantics-directed compiler synthesis. No one quite knew what it was. And after several talks, Reynolds leaned back and said, you know, in most hard sciences, the researchers look for profound theorems. But here in computer science, what we should be looking for are profound definitions. And so if you pause and think about it, why do we need profound definitions? And the answer is more or less because we're such a young science, we're not quite certain where we're starting from or where we're going. And 100 years from now, if computer science is going to be taught as a hard science, we need some foundations. And we need these starting points that we can teach young researchers. And so we have to find those. We have to find those profound definitions. The second remark I wanted to repeat from Reynolds came about 20 years later. I was at a workshop, I think in Portland, Oregon, around 2000 or so. And it was a long day of technical talks, people doing their little fiddly stuff and some new little construction. And by the end of the day, everybody was tired. And Reynolds just gave this big sigh and said, you people, you're always inventing new areas with new terminology and new methodology. You would do so much better if you would try to unify existing areas and simplify them under a common terminology and a common methodology. And I think we've all had that feeling when we've seen technical talks that it sort of looked familiar, didn't quite fit in, but boy, it sure seems like something I've seen before. And that's another goal for computer science to try to do, more unification and simplification. And I was planning to talk about this at the end of Bernhard's talk because what Bernhard's going to be showing us here is the fruits of this idea of unification and simplification. When he went over to Edinburgh after finishing his thesis work in Kiel on data flow analysis, he was ready. He had big eyes and big ears, and he could see the connection between that and the kinds of property validation the Edinburgh people were doing with the concurrency workbench. And there was a unification of these areas, and there was a simplification of the constructions because these two areas really could be put together. And what also happens is that when you do that, you inevitably unwrap the subject areas and you get into the basic definitions, the profound definitions which are driving this research. And this is the sort of thing we should be looking for when we do research. When we do this unification and simplification, we unfold and we find these definitions. And I think in a more general sense, I'm getting near the end of my little comments because it also looks like Bernhard's about ready to go. Is that right, Bernhard? Are you about ready to go again? Looks like
I'm ready. Perhaps during the talk we can switch it on again. I have sometimes trouble if there are too many icons on my screen. I'm not sure why I have a quite good computer, but collapses when there are too many pictures.
Okay.
Perhaps is it possible that
Let's-
we reunify at the end and I just talk now? Is it okay? I will also
You go
switch
now.
off my picture.
Let's
but-
just, sorry, let me just break in here and just, I think David was about to, would you like to wrap up what you just said and then we'll switch over to Bernhard again, or?
I got a couple of sentences. Just I was going to
Please
say,
go ahead.
with regards to VMCAI, we have a similar issue. When Tino Cortese organized VMCAI as a conference series, he wanted to bring together and try to unify these different subject areas in the conference title's name. And in doing so, hoping that somehow we could gain some sort of simplification and some profound definitions, foundations about what we do. And so I think we're seeing this reflected in kind of the summary Bernhard's giving us today. So I'll give it back over to Bernhard and we'll see if there's any time left at the end.
Thank you.
Yep, thanks.
Bernhard.
Okay. So I switch first my video out, so this might help, and will now share again screen. Check. Now I have to go again here. So thank you very much for being back. Sorry for the trouble. So we were just there that just by SOS, you could transform this thing, which is kind of the worst case example for redundancy eliminators, totally. Here you have no partial redundancy anymore at all. And of course, then there's some other redundancy in structure, which you can eliminate by minimization. So, and partial redundancy, I put it here, is exactly a notion that says a computation is partially redundant at some point if there is a path to that point where this computation has already been done. So, and you see here, I mean, when you are here at this position, you know there is this path where you had it computed already, and here you had this even twice on one path. So this is partial redundancy. Classical computations cannot address that at all. Just these SOS on that particular on that domain totally eliminates the problem. Okay, my favorite example, which is from my PhD thesis, is this very one-state automata here, this one-state program, which is highly because it can loop and it's highly redundant if you have more than 2 steps. And this can be also computed into something where you are totally redundancy free. And in fact, the partial redundancy elimination was the problem which I took over from my PhD thesis, which took a long, I shared a lot of time with it, and which was also the reason for developing this data flow analysis as a model checking paradigm when I learned about model checking. And so let's come to the second domain-specific language. And there we look just at this example. I just want to illustrate to you what is the benefit of using LTL as a domain-specific language for specifying static analysis. And so we will compare the normal thing, the first thing where you use LTL as specification language and an execution environment based on model checking. Then we look at the classical solution of Morel-Rangwas. And finally, I will show you that this LTL specification is so simple that you can solve a problem which people had for a long time, which is called register pressure, and which now is very easy to solve simply by changing the mindset. So here's just a picture, a very old picture, 25 years old, where you can see the idea of a partial redundancy elimination in the sense of Morel-Rangwas is that there are points in the program where you can, in principle, compute values without changing the semantics of the values of expressions. These areas have kind of early borders where you can't move the computation up any longer. And the idea of Morel-Rangwas was, let's compute always at the border. Move things up as earliest as possible. You have computations in that program, and when you move the computations up, store the value and use the stored values, then you can cover these partially redundant computations, and there's an optimal solution to it. So, and let's look at that now. Here's linear time temporal logic. Actually, is a tiny little bit special because we have here with this B, we have a backward modality, so we can speak about backward and forward computations. And I don't want to say so much about the semantics. I hope most of you know it. So you have something like the next time operator. So if you have here a step, here this state satisfies next f if after a step f is satisfied. And then we have here the other fundamental operator. This is the weak until. So at this point, f weak until a holds if f holds until a holds. So weak until means there's no way to leave the area where f holds without passing a. This is what this does. This is the only, you don't need to know more about the intuition of linear time Ramble logic. And now you can specify on this simple slide, this is the entire algorithm or the entire specification of the Morel-Renvoise algorithm. You will see what was the original formulation in the end of the 70s. And now look what's here. One thing is there's two simple properties. Where do you want to compute? One thing is you don't want to compute at a spot here where the computation suddenly is not used at some continuation. Whenever you compute it somewhere, you want to be sure that this computation is going to be used. Otherwise, you would have introduced a computation on a path where it hadn't been before. So this is the one property, don't safety. You can specify that in the logic like that. I don't want to kind of spell that in detail to you. Just keep that picture in mind. Downsafe means that you find if you start computing, you won't change the operands until you really use the computation which was in the original program. And the other thing is then this earliest property. I just told you that the idea of Morel-Renvoise was to moving computations up. They called it hoisting. And so but when is something earliest? This is this spot here. If you can't move it up without violating the first property. And now the entire specification is just a conjunction of the two. Even if you inline these two expressions, it's still a one line specification. And in fact, it's algorithmically more efficient. It uses only maximal fixed points and negations thereof afterwards. So, but it's very modularly separated, and it is one forward and one backward computation. So it's very well structured, and by this also very nicely to compute. And now let's just look at the Morel-Renvoise formulation. I just go through it. Explaining it doesn't make sense. So this is the first page. Second page, you can see in this, let's say, big trunk of equations, you have both minimal and maximal fixed points. This is the meet, and this is a join operator. So you have within one equational setting, you do that both and in the intermixed fashion. And you have, as you can see here, both backward and forward computations. So it's complex, and it is 1, 2, 3, 4 pages. This is a specification of the algorithm of Morel-Renvoise. If you now come to the proof, if you want to prove that the transformation is correct, I mean, I really suffered very much on proving that on the original or on following the proof provided by Morel-Renvoise. If you try to prove correctness based on this definition, this is an easy exercise for every student. And it is even possible to prove optimality, which never has been shown for the original framework. Okay. So, and the other thing I wanted to tell you, so if you have such a simple setting, if you are living in this new domain-specific language for static analysis, it's very easy to do more. I should go back here. We have here lazy code motion. One big problem for code motion was, or for the Morel-Renvoise or other approaches to eliminating partial redundancy, was that it increases register pressure. In fact, it is even maximal concerning register pressure, because we move computation as far up as possible, meaning as far away from the original computation as possible. So, and now by just having one additional predicate, I don't want to go through that detail. It's the same pattern again. Just by adding this additional, by having this additional predicate and building this conjunction, so just this predicate, and this essentially means that by going down, yeah, I'm at the earliest computation, I want to move down to such a green spot. When I go down, I shouldn't miss any original computation. So what we say is, we have this the optimal solution in the sense of Morel-Renvoise with this earliest computation. We want to lower the register pressure, meaning lowering the computations, trying to get down here, but we shouldn't miss any computation. And a thing is delayed, one of those nodes is delayed if going here doesn't miss anything. So the path from here to here don't have computations. This is essentially what it says here. And if you then build just this conjunction, you get, in fact, the unique solution, the optimal solution, which is computationally optimal and at the same time register optimal. So you have the least register pressure you can have here. Okay, I just wanted to show you this idea on the level of how you compute on some kind of bit values, as you have done it here, never brought people to this kind of simple setting. Here we have just three simple predicates and everything comes out. And for me, this kind of, yeah, this was an eye-opener for me. And this drove my whole research afterwards, that with the correct language, of course, very much in this sense, very much constrained. So temporal logic is not computational complete, but it is a very strong method for certain purposes, for example, for those kind of computations. It's always the case, of course, when you have a domain-specific language, and we are talking, or I want to make a big claim for them, is that the more specific the language, the better properties you have, and the more guarantees you have. And to make that even clearer, we have the final domain-specific language, the Backus-Noah form, and there we want to address language refinement. Backus-Noah form is used to, of course, for syntax descriptions, and in fact, playing with syntax allows you to guarantee properties already at the meta level, at the syntactic level. We have also other constraints, but it's already sometimes surprising what you can do just by looking at syntactic constraints. Okay, as an example, we want to look at a very small language. This is PL0. It has been proposed by Nicholas Wirth as an educational language. Of course, what you see here again, it's a BNF. So BNF is everywhere. It's used all the time. And what we can do now is, and this is another kind of connection which we saw recently. Okay, we have BNF. We look at syntax definition. On the other hand side, I developed also something which was called context-free model checking. This was model checking of context-free processes, of procedural systems or procedural automata. And okay, so we can in fact transform the world of BNFs into this procedural automata. And if this is even very simple, and it only needs a very simple BNF, it needs a very simple BNF. This one single rule transforms your BNF into these kind of procedural automata, and they are similarly, they are an equivalent expression of the same information. Okay, this is part of it. So we are transforming the Nicholas Wirth PL0 language into our process systems or process automata. Here we have the statement. Also for statement is one of the known terminals in that language description. And here you have, for example, the procedural automaton for that statement. And this has one peculiarity. This is this green edge, because we modify a bit on the BNF. So it's not just BNFs as we know them, but they have stuff which is optional. We indicated here, we could have done it on the textual description also, but let's do it here. We say this green dotted line is a may transition. It's known from people who verify process systems with label transition system, no modal transition systems. This is the same concept. You have here a may transition. That means, or what should it mean? We have a language description. This dotted line means a language which conforms to that specification may or may not support that call. So there can be a language which doesn't support the call at all, but there may be also one which supports the call. So in essence, the BNF with may transitions doesn't describe a single language, but a family of languages. And the members of the families arise by choosing what to do with those may transitions. And in fact, on this BNF level, we want to do some kind of language engineering. What we do in our example is we introduce a new, this is just for convenience and to show that better, but we do that frequently in our tool also. We introduce a new non-terminal as structural element in order to get a handle on, on a better handle from the outside on the structure of the language. So here we have this decal doesn't exist. But of course, the structure, which is just an abbreviation for a structure which exists in the original specification, which we abbreviate by decal. This is just a very simple transformation on the BNF, which is semantics preserving. And the language engineering continues now by really doing something which might change stuff. So we go from, so we refine essentially the language of described the PL0 with these dotted lines. And a step which we want to look at is the following, which is indicated here by the red arc. From the start node, we may have a declaration and then a statement. There may be many declarations. But there may be also way without declarations. But statement contains call transitions. So there is, of course, a path where you can come here via const, for example, take a statement, make a call, and you will never declare. And the problem we want to look at, I mean, this is all slightly simplified here to do it in this short time frame. What we want to guarantee just by language structure is that with a program in that language can never have a call to a procedure which has not been declared. So we want to make that, which is a typical static semantic feature, which you can compute otherwise, but you can transform that into a syntax feature so that even the syntax checker is already aware of it and guarantees that this is not violated. And this can be done essentially by this kind of language refinement. So essentially what we do is, as long as we don't do a decal, we do not allow in statements the call, we just take it out. You may look at the slides, they will be available and follow the details, but this transformation now guarantees that whatever program you have, there's always a decal before you have a call. So now we look at it really from the property point of view. We want to introduce, we call it Archimedean points. These are properties which are guaranteed by the language, something which the language gives you without further, you don't need any further constraints or anything. It's just provided by the language. And we look at a number here for properties. So we have 4 properties. This is here written in the mu calculus here. For these two, you have also a simple CTL description. And of course, we are here again. I told you we use all these domain-specific language frequently. We use here a pattern of temporal logic. Here it's a branching time temporal logic, also very, very powerful as a mu calculus. CTL is much weaker but easier to read. So in many application areas, you should use CTL because that language is too powerful. And here a brief description of what is, so that you get an intuition of what is meant here. So here it says, it's not possible to see a call before you saw procedure. Procedure was the indication of a declaration in the syntax, the original syntax given by Nicholas Wirth. So this essentially says, A says, I cannot see a call in the program description when I didn't have a procedure declaration. This simply says, the second one simply says this is possible to eventually, it's always possible to eventually reach a call. And this says it's possible to eventually reach a declaration. And here at the end, you have, whenever you saw a procedure declaration, it's possible to eventually see a call. These are 4 properties. And now let's see what happens to these properties when we refine in a kind of systematic way. Okay, one thing which I should tell you, these properties can be model checked, but yeah, on what do you want to model check? You need an underlying structure, and the semantic structure underlying is an infinite state transition system, which is specified by means of that set of SOS rules. You have again a set of SOS rules. This is just structured operational semantics, which by means of a stack mimics the entire kind of recursive structure of the language definition. And then you can, because we have context-free model checking, you can on that you can verify properties that correspond to these kind of infinite state structures. Okay. And here an overview, we want now to show that our language engineering framework gives you nice properties for refinement, which is in particular property preserving. So we have here 11 variants of languages. This is just the full while language. This is, and here we have, we indicate with a D, the capital D says there must be in the language the possibility to declare. The capital C says that the language definition guarantees that the possibility to call. And okay, these are all still not, also everything which is small language is in fact not yet a fully defined language, but still have some weakness, some kind of made transition. So because the capital letters, they indicate strong classical transitions, and that the lowercase letters indicate made transitions. So you have here, it's probably better than to explain it here. You have here a kind of lattice of language refinement. You have here the language where you may do anything, call and declare, but you are not required. In this set, in this specification, you cannot answer any of the 4 properties. Yeah, because there are refinements here. Down here, you have the real true refinements. These are the real language you can at the end have. The full while language and so on. Here, these are the language where everything is defined. There's no may anymore. These are fully defined languages, in a sense, the classical syntax definition as we know them. And everything up here has some potential of refinement. So this is more than one language, a set of languages. Yeah, and question marks mean I cannot decide because in my set of languages I describe, there's both. There's an example and a counterexample to the property. And what you can see now here is in this lattice of refinements, and it's well known that this modal refinement which we did here, this is kind of swapping or treating the may transitions. We have a preservation of branching time logic, so it's or even temporal logics. Any temporal logic is essentially preserved by that. So in this scenario, we can, for example, see for the full set where we can do whatever, nothing is clear. What we can see here is this T here indicates the transformation I've shown you. This where the transformation with a solid big arc, this transformation. There we see this is a very powerful transformation because the first property is guaranteed. Everything below here guarantees the first property. So I have a language family where it's always clear that there's no way that you can have a call without a declaration. So these kind of things can be all done just at that meta level. But it's a very complicated topic, and I cannot go too much into detail. But what you can see here is by means of now this BNF thinking, or if you like, a procedural transition system thinking, combined with the notion of refinement, you get a very powerful language refinement concept. And this is very helpful when you design domain-specific languages. For example, if you want a language where it's really important that certain properties hold, you can very often make them what we call a rigid Archimedean point. We can make them part of the syntax. You cannot do it with everything, of course, but you can do it with quite a lot. And sometimes it makes sense. Yeah, okay, you can, if you make enough restrictions, you can always enforce properties, but then you, of course, always have to bargain with the expressive power otherwise. Okay. Here's for property preservation. So this was, but good news, this was everything I wanted to tell. So what have we seen? We have seen that there's, we have looked at 3 families of domain-specific languages. Yeah, and I call it families because it's really, if you like, it's really more like patterns. Yeah, the BNF patterns, the SOS patterns. They are so different variants that you cannot just say that is a language. And there are entire conference series just devoted to SOS and expressiveness. So this is not the point. It's just the idea of step pattern. And for temporal logics, there are many, many variants. And we have good experience with the kind of thinking switching to the logical level. So these are very different mindsets behind those 3 language domain-specific language patterns. And I profited a lot in my research from kind of really thinking about these kind of patterns. And let me just put this as a kind of final remark. So what I learned, or what I took out of my experience, in particular when I first observed this connection between temporal logic and specification of static analysis, or between data flow analysis and model checking, was the point is this change of mindset, this change of thinking in terms of how to compute to something what to compute. The good thing is, and why is it so simple to specify, for example, the partial redundancy elimination at the what level? Because you can simply combine, in this case, properties by conjunction. It's not possible for algorithms. Yeah, the conjunction of algorithms is a complicated thing, but in properties, conjunction is a basic concept. And as we have seen, in essence, we have only a very simple propositional logical structure on top of simple predicates. And these are very small formulae which give you a lot away. Of course, if you want to do the step towards execution, yeah, then you have to add the whole knowledge of model checking, then you add a lot of stuff. But the good thing is, yeah, model checking is a well-known concept. In a sense, by using that what description, you kind of reuse as commodity the idea of model checking. You don't worry about how to do that. You just worry about what you want to do. And I think this is an important point when you are developing domain-specific language. This is the way to focus on what you want to do and to take as commodity as much as possible, to kind of distribute out complicated things which are solved already. So it's a new level of reuse. Okay, and here in this case, what you can see, what we got of it, very easy proofs. We use very often synthesis. One kind of synthesis is to really synthesize from the domain-specific language, LTL, the concrete data flow analysis. You get meta-level guarantees. If you use temporal logic for specification, you have certain kinds of things that certain things will terminate. You know about the logic stuff, which you wouldn't know if you just write equations on some kind of domain. You have much more structure, and that structure gives you guarantees at the logical level. And and then you have this, what we call meta-level reuse, is we reuse this entire concept of model checking. And this makes it so easy to specify, for example, what partial redundancy is like. And as a consequence, you get very well-structured and powerful tools. So this is essentially my message for the day. And perhaps just as one picture which you can take for it, we are using these ideas quite a lot. Fritz told you that we are doing industrial projects. We have a language workbench also, and this language workbench is for graphical domain-specific languages, and we have numerous applications where we use this concept of reuse in terms of domain-specific language in practical scenarios. Thank you very much.
Thank you. Sorry. Oh, thank you, Steph. Bernhard.
Yeah.
Thank you.
Yeah.
And let's just applaud the Zoom way. So. Well, sorry, I hope I didn't interrupt, but maybe Dave, you wanted to, conclude some things or be open for discussion or questions, both from this is a rather philosophical yet very technical talk. So this is exactly what I found exciting about your collaboration.
I think I said the main points earlier while Bernhard was doing his repair work, and the conclusion slide just emphasizes that if we can dig down deeply enough into these fundamental definitions, we find all of a sudden all sorts of other application areas present themselves. Not much else to add to that.
Thank you. So questions, please, floor is open. And my suggestion is please unmute and I'll check what we have in terms of questions, if any. Oh, I've been logged out. Okay. Nothing on Clouder. So please go ahead, just unmute if you have comments or questions. Maybe I
have
John.
Yeah, this is John Gallagher. Yeah, you mentioned in passing, Bernard, but thanks for the very interesting talk, by the way. Really inspiring. You mentioned in your first part of the talk when you were talking about control flow analysis that it was basically partial evaluation of the semantics. Yeah. And I'm just wondering, do you actually use partial evaluation or partial evaluators as in your tools, or is it a sort of abstract idea behind the way you do things?
We make continuous refinement of languages by partial evaluations. Yeah, what we do very much is partial evaluation at a kind of meta level by introducing concepts of a language, kind of freezing that in a very simple way. So, for example, we have a language which data domains and with control domains or process domains, and sometimes we just partially evaluate a given data structure and only consider in the future the scenario which is given by that structure and kind of freeze essentially input and making the continuation of system development simpler by having that set. So essentially it's an instantiation process, and it uses really partial evaluation. You really try to get, for example, the entire knowledge about your class diagrams which you fixed into the language and make a very simple tool, for example, for just dragging and dropping process graphs, and the data are kind of dealt with automatically.
I see. Thank you.
I think we should thank both Bernhard and Dave again. Thank you. Thanks for coming and being here and giving this presentation and discussion. There's a discussion possibility still in the break in half an hour, but for now, let's move on to our topic. And Reina is going to be the session chair. So welcome, Reina.
Hello. Yes, welcome to the applications session. The first talk will be given by Yahui Song, who will present a synchronization effects logic for temporal verification of pure SRL.
Okay. Yes, thanks for the introduction. So far I cannot share the screen. Can I? Can you see my screen now?
Yes.
The slides?
Yes,
okay.
I can see that.
Okay, thank you so much. So My name is Yahui Song. I am a third-year PhD student from National University of Singapore. I'm really happy to have the chance to present my paper here, which is also a joint work with my supervisor, Prof. Qingwei Nan. So talking about the title of my paper, so it's asynchronous effects logic for temporal verification of pure Astera. So our target language is Astera, and we are trying to do some temporal verification. Also, we design, also prototype this logic, which we call it synchronous effects in this context. So firstly, I will introduce you what is the Astera language. So Astera is one of the synchronous languages. It is mainly used as a system design and a kind of a modeling language. To some degree, it's already a specification language itself. So here is a piece of a code of the Astera program. What does it do is it declares a local signal S1, then we check the presence of the S1. If S1 is being emitted at the current time instance, I will emit S1, else I do nothing. So it's just an example of the program. Then Astera has a well-established deterministic semantics. Also, so this one is for the main feature of the synchronous language in general. So primitive constructs execute in conceptually 0 time, which means that if you emit 2 signals in sequence, they will be shown in the same time instance, and they will be assumed that to be happened simultaneously. Except that if you explicitly use these pause statements, you will jump from the previous time instance to the next time instance. I will have an example for that later. Then there are 2 critical problems of Astera program. The first one is the correctness checking, and the second one is the safety issues. So looking at this piece of a code, this actually is logically incorrect. The reason why it is logically incorrect is this local signal S1 can be possibly present, also absent. So for example, if you are assuming that S1 is present, which is already being emitted by someone else, then you will emit it again. So you are kind of like re-examine the presence of S1. Else, if S1 is absent, you will do nothing, which keeps to the default value of the signals, which is absent. So this kind of program is logically incorrect and is mainly being targeted to be checked out by this correctness checking. Right. So next, I will just go through our techniques and see to introduce you that what we do, and I'll show you what is the benefits of that. So the first part of our techniques is the specification language. So if we look at this program, here is a close module. So the program is very simple that I will do a pause first and will emit a signal which is called close. Then we annotate the specification in the command line in green. So what does it say is we define the precondition and the postcondition. In the precondition, we require that in the current time instance, by the way, we use these curly braces to represent the time instance. Then in the so it's the precondition actually says that before you enter into this module, the current time instance should have emitted this open signal at somewhere before you enter into the program. Then what we guarantee is defined in the post condition, which says after this ensures, we will ensure a sequence of 2 time instances. The first one contains no signals, which means we don't guarantee any signals will be happen at the first time instance. In the second time instance, we ensure that the close this signal will be emitted. Then here is a slightly longer program, which is called the manager module, which calls this close in the middle of the program. So what does it do is it declares a local signal open first and get into a loop. Inside of the loop, you emit the open first, then you examine the presence of this bottom signal. If button being pressed, being emitted somewhere else, you will run this close module in the Zen branch, else we do nothing. Then we exit the presence statement, then we get back to the loop again. Then these are the specification of this current program. So in the require, we don't put anything here. Empty time instance means that we don't require any happened history traces before you enter into this program. And we use this disjunction notation to represent that this trace all the other one. Then we use this clean star to represent the repeated trace. Okay. Then next one, I need to present you our forward verifier, which is used to accumulate the effects from the program. So this piece of the code comes from the previous manager module, which is the loop. If we take it out, what we see is we initialize the system states using an empty time instance. And whenever you get the emit something, you add these events into your effect state. And before you run this program, you will need to check that the current program states, the trace satisfy the precondition of the colleague function. Then if it succeeds, I will concatenate the post condition of the colleague function into my current program state. That's why we got so we started from this open and bottom, then we check the precondition actually holds. Then after we check the precondition, we concat the post condition of this close to my current program state. Then we define all the forward rules for different kind of syntax of Astor programs, which we have a core language defined in the paper. Then after you accumulate the effects from your your current program, we would like to check the post condition holds at the end of the verification. So normally we put the post condition as some like kind of temporal properties that we want to guarantee. Okay, then the last piece of part of our work is a term rewriting system, which is a purely algebraic decision procedure to check the entailments or inclusion relationship between two effects. So for example, if we have a phi defined as this is what we just got from our previous slides that we accumulate from the program, then this is our post condition that we define in the specification. Then we want to check the inclusion holds, which means that all the traces generated from the program will fall into the set of the property that we want to guarantee. So we do an unroll. So here we have a disjunction. So we unroll this iteration because clean star means that it's a repeated trace. We unroll it once so that we get either this piece of the code concat with the phi, or this single instance concat with the phi. Then at some point we do the elimination to do this unfold. So we unfold the closed instance from the both sides. Then we have a normalization. For example, the empty trace disjoint with false will ends up with empty trace. So at some point we will see that this formula actually reoccur. Then we will prove the inclusion using this reoccur rule. We also define those reoccur unfold rules in the paper. So why do we need to use this kind of logic, and what are the main benefits of doing that? So I think the benefits come from what's the needs from coming from the Astor program. The first one is a logical correctness and the constructiveness checking. So there are different semantics of Astor and doing this logic correctness checking, but it's generally not complete in the sense that some of the code actually is logical correct, but the compiler will reject them as incomplete. So what we do is we also adding the path constraints into our program states. For example, when we check if S1 is present in the then branch, we will adding the path constraint here, and we're adding what is the real happening in the right hand side. Then we conjunct them together. So we will list for this piece of a code, we use this kind of techniques to do this logical correctness checking, which actually is a 4C of the signal, which makes the correctness checking more complete. Also, the previous techniques cannot deal with this unbounded input value, whereas in our techniques, it is able to be checked for the input signals. Now, another needs of these kind of techniques is the temporal verification. So previously, these two kind of checking, like correctness checking and temporal verification, is being done separately. Now, what is in the temporal verification, traditionally, what they do is they use this LTL formula, then they translate this LTL formula into Astro program, which violates the safety property. Then they compose this violates safety formula Astro program with the given Astro program. Then they rely on the compiler to do some analysis of this temporal to check the temporal properties. Whereas in our method, first of all, we because we have the decision procedure, so we don't need to translate our temporal properties, such as maybe LTL, into automata. Then because we avoid this kind of translation into automata, we actually improve the efficiency in the sense that we disapprove the properties earlier. Because previously, if you have a failed entailment, you still need to translate it into automata. Then this kind of the time can be saved actually. And we have this scalable expressiveness for temporal properties. For example, this is our current work. Is also a free future work for this current paper, which is you can add this kind of dependent values into your iteration. So if you add this n, so n could be a value from your input program, then you depend on your input value and you say that this actually iterates n times. So it's it can be, the expressiveness can be scaled. So we do an implementation, a prototype system in OCaml, which is the open source system. Then we do the evaluation based on two benchmarks. The first one is the open source compiler. The second one is hiphop.js, is a domain-specific language designed for JavaScript for web applications. And we take a subset of their benchmark and do our experiments. Yeah, when we do the experiments, we manually annotate the temporal specification for the programs and do the to do the verification test. So in summary, what we have done is the first thing, we define the syntax and semantics of our specification language, which is called synced effects or synchronous effects. And also we derive this kind of automated verification system by defining a horror-style forward verifier and the efficient effects inclusion checker. We provide a prototype system, also provide experimental results and case studies to show the feasibility. With that, I would like to conclude and thank you so much for your attention. I will be happy to take questions.
Thank you for the interesting talk. I think in the interest of time, we have time for a couple of questions. If you have a question, please unmute yourself and just ask. I don't see any questions on Clouder, but you can also ask there. Okay, if there are no questions yet, maybe I can start. So I wanted to ask about the annotation overhead. So you said that in the experiments that you carried out, the programs were manually annotated.
Right.
So how much is the annotation overhead in terms of the size of the programs?
I see. So what we actually do is there are a bunch of like LTL properties. So we translate the LTL properties in using our logic, and we just randomly, we actually hired like a RA undergrad student help us to annotate these programs. And we in total we had like almost 100 of programs. It takes the student like maybe 1 week to annotate the specifications like that. Yeah.
Thank you. Are there other questions or comments? Okay, then yeah, you can ask more questions in the break, and afterwards in the chat. And in the interest of time, we can proceed with the second talk, which will be given by Youngmin Kwon, and he will talk about the design of a GPU-based quantitative model checker.
Hi, I'm Youngmin. Thank you very much for the introduction. I'm trying to show my screen. Is it shared?
Yes.
Hi, everyone. So today I'm going to talk about designing or applying model checking techniques to automatic control problems. So using GPU. My name is Youngmin Kwon, and this is a co-work with me and Yoon-hee Kim. So let me start with the definition of the system that I'm going to use. It's, we are interested in controlling linear time invariant systems. As you know, linear systems respect the superposition principle. That means if this is the input and that's the output, and then I guess if you add another input, if you add these two inputs, then this output is the superposition of these inputs. And in addition, if the system is time invariant system, then its response doesn't change over time. So you can apply this convolution sum of impulse responses to get the output. So basically, if this is the input, then your output can be the convolution sum of these inputs. So that's the linear time invariant system. And I'm going to define it more formally. The linear time invariant system is this 7 tuple. Here, U, Y, X is a set of input, output, and state variables, and A, B, C, D are system matrices such that these dynamics equations are satisfied. So here, this boldface X, U, and Y are the input, output, and state trajectories. Okay? And using them by just making the Cartesian product, I'm making this computation path. So if you look at it, this computation path is, let's think about this linear system of helicopter, for example. So here, if I apply this input, that is the rotor angle change here. If I change the rotor angle that way, then the pitch and pitch rate of this helicopter is changing like this. So combining them, this is one computation path. Right? So if I change this input, then we'll get different pitch and pitch rate changes, the different trajectories. So as you can see, there are uncountably many trajectories. And then for each of them, I would like to check whether it satisfies LTL formula. Okay? So this formula can be, this recurrence equation can be rewritten in this way. If you look at it more closely, then this is the convolution sum part, and this is response from the initial state. So basically, you can write the state and output trajectories in terms of the input and initial state. Okay, so that's our model, and this is our temporal logic. It's called linear temporal logic for control. It's basically an LTL. It has all LTL operators, but its atomic propositions is about linear inequalities about input, output, and state variables. So it's the atomic proposition. So this is the syntax, and the semantics of the LTLC is very similar to LTL, except that the atomic propositions are evaluated. It's basically the linear inequality with the variables at the trajectory. So this pi is a trajectory, and this is the VI is the input, output, and state variables. And from the trajectories, we get the real value and apply it, replace the variable, then we can get the truth value of this inequality, right? So that's about our that's about the atomic propositions and the time advance in this part. For example, let's just see this next operator. So given this path, the computation path, next pi means, next phi means, and next step phi is true. So really in this trajectory at this next step, this phi is true or not. That's how the time advances in this computation path. So that's about a single path. So if you look at this quantitative model checking, then most of the model, many of the model checking techniques are based about this single trajectory from the input, from the initial state to a certain point, whether that path satisfies the LTL property or not. Those are most of the approaches. Here I'm trying to check all trajectories. I'm trying to check against all trajectories that are, and if you change anything, like the input or initial state, there are different trajectories. So there are uncountably many of them. So I'm going to check this, but because there are too many of these, I cannot enumerate them. Instead, I'm going to convert the atomic propositions at future time in terms of the initial state and the input. And then I do the linear programming to check whether there is a path that may satisfy the constraints. Okay? So that's what I'm going to do it. So because we cannot check this infinite path, instead of many approaches are using this bounded model checking. So it checks up to certain points, but instead of doing this, I'm adopting these horizon constraints from model predictive control. The horizon constraint means after the output horizon HY, the system reaches the steady state. So the trajectory doesn't change. So it means if the input doesn't change from the input horizon, then input is something we can apply. So it's a kind of free variable. So we can free to freeze the input. It doesn't move after HU. And at that state, if the state doesn't change, two consecutive states doesn't change, then the system reaches the steady state. It doesn't change anymore from then on. So with that constraint, we can remove all temporal operators. For example, next P is equal to P, because the P doesn't change. P until Q is equal to Q, and P release Q is equal to Q as well. So with the horizon constraints, now I can remove all the temporal operators. And then that means I can convert my LTL formula into DFS, disjunctive normal form. Right? Without any temporal operators, I can convert it that way. So let's just see how model checking, instead of going through the model checking algorithm, let me just explain a brief model checking algorithm. Here is my system model with two states, one input, one output, and this is the system matrices for the system dynamics. The specification is H is the horizon constraint. It is implicitly given. If H is true, then I'm going to check this formula. Like many model checking algorithms, I'm going to find out the counterexample that satisfies the negation of the specification. That will be H and next A and next A. Right? So that means I'm going to find the computation path pi that satisfies this. So if I just convert it this way, then we have H that is composed of input horizon constraint and output horizon constraint. So this is the output horizon constraint and input horizon constraint. And we have these two parts, next A and next A. Next A is Y1, step 1 is less than 3. Next A means Y at step 2 is less than 3. Right? So this is also, this can be rewritten in terms of the input and initial state using this formula. by applying the recurrence equation, I can convert this into this form, in this vector form, where this vector variable v is initial state and input u0, u1, and u2. Right? So this formula can be converted into these vector form conjunctions of linear inequalities. And if there is any v that satisfies this, that is the pi. That can, from there, we can compute this pi, the computation path. That will be a counterexample. Mm-hmm. So the model checking problem is, and this set of inequalities, conjunctions of inequalities, can be solved by linear programming. The feasibility of these can be checked by linear programming. And if there is any feasible solution, from that solution, we can find out the counterexample. So whether M satisfies pi can be decided by this model check, the linear programming problem. Right? So for this simple example, we have only one conjunctive terms, but in general, the DNF, if you convert the LTL formula into DNF, there are a lot of conjunctive terms, and we can convert them into DNF. And the satisfiability of the entire formula can be checked by checking each of these conjunctive terms. And that can be checked by linear programming. So we can convert LTL program into DNF, and then the satisfiability of this LTL formula can be checked by linear programming on each of these conjunctive terms. But the problem is there are exponentially many conjunctive terms in our DNF, so we need a way to speed up. So we are using the GPU devices to increase the degree of parallelism. But suppose that this horizon is like 40, and the formula is always A or B, then it will be like 2 to the 40 conjunctive terms that cannot be checked easily. So the increasing the degree of parallelism alone cannot solve this problem. Instead, we would like to check whether there are common expressions in these conjunctive terms, and if there is an infeasibility found in these common expressions, then we can discard the entire conjunctive terms that shows the same the common expressions that's infeasible. Right? So the problem is then how can you find the the common expressions in these conjunctive terms? The answer is we just unroll the Bucci automaton. Then each of these depth first search will make a conjunctive term in a DNF. Right? So at each step, we check LP up to that path. If there is an infeasibility found, then we can skip the subtree starting from that infeasibility. Right? And in GPU-based model checking, we would like to combine these two. So instead of checking LP at every step, we check like every 10 steps. We will build path fragments for every 10 steps. So if the branching factor is 2, then it will make like a 10, 24 path fragments. And we bring these, put these 10, 24 path fragments into a GPU and solve them in parallel and eliminate those paths that's not feasible. And only those feasible paths, we will build another 10, 24 path fragments and put them into the GPU to solve them in parallel. So this, we call this mixed DFS BFS algorithm. We are using this. With that technique, we can use the pruning technique as well as utilizing the massive parallelism of the GPU devices.
I'm sorry, but we are running out of time, so you would have to stop and take some questions.
Okay, let me just briefly explain this really quick. So this is a helicopter example, and our goal is to accelerate the helicopter to VF and then decelerate it to 0, stop. So if we helicopter will initially stop, if we increase the VF, the problem will become difficult, more and more difficult, right? And if you increase it too much, then the problem becomes obviously it's not possible to reach that speed. So if you run this program, initially it's very easy. So you can solve it easily, and at some point it becomes difficult, and then obviously it becomes easy again as you increase the VF. So these two graphs compares the CPU with GPU. The red lines are the GPU performance, and the blue lines are CPU. If you look at it, the fluctuation, the variance, the performance is low in GPU, but it's large in CPU. And for the easy problems, CPU wins, but as the program becomes more difficult, GPU wins. That's what I found. I guess the conclusion is just what I explained. I can take questions.
Thank you for the talk. I think we have time for one question perhaps, or two. Are there any questions? So yeah, maybe I can start with I don't see any questions on Clouder. So if you have questions, just unmute yourself and ask. Otherwise, I will start with the question. So can you maybe comment on other approaches that use, or do they exist other approaches that use kind of GPU-based techniques for model checking for this or other types of systems?
Yeah, there are only two systems I saw about using GPUs, and most of them try to increase the parallelism using like a DFS search. Right? They put as much computations in parallel to the GPU. But as you can see in our approach here, we need to check. I mean, at some point we have to prune some passes that's infeasible. Otherwise, because of this exponential growth of the computational path, we have to check the 1,000 cores or 2,000 cores doesn't match for exponential growth. And that's what I found.
Okay, thank you. Any other questions? So if there are no more questions, then we conclude the session and proceed with the break.
Thank you.
And thanks again, the speakers.
And thank you all also. Thank you, Raina. Just a brief reminder, two things. The first one, there was a question actually for Dave and Bernhard, if you want to continue. But please also, there are two polls on the Clouder. Just scroll up and please fill them out at your convenience before we end today. Okay, thank you very much. And there's meeting rooms on Clouder, and we can also stay here if you want to. Is Andreas here?
Yes, sir.
So Dave and Bernhard, I think, are still here. So maybe you wanted to, Dave and Bernhard, are you still here? You're gone?
Mute.
Bernhard is there. He's just
I'm here.
Yes, excellent. Yes. So maybe you want to, pose your question, Andreas, yourself. Yeah.
Yes, I had a question for Bernhard. Is Bernhard? Bernhard is still here, but he has not switched on his video.
Yeah, I'm trying to dial. Here I see it. I may get it.
I don't want to ask a question to the person whom I don't see,
Okay.
Yeah.
If you want to see somebody, you want to see his face, yeah. Okay.
So my question that I put on the Cloud channel, and you saw it later, Fritz, or?
Yeah, I'm
Sorry?
sorry. And
Ah,
there
you
was
saw
time.
it.
We also had
Yeah, yeah.
time issues. So thank you. Yeah.
So my question was actually two questions. One, the question that I posted was about LTL. So in the work that Dave and Bernhard you had together, you did not use LTL, you used CTL, right?
Yes.
Yeah. And it seems more natural to use CTL because, I mean, and this leads to my second question, because everything is based on fixed points, right? I mean, it seems to me that the game you are playing is that you have logic with logical connectives like conjunction, but to make the whole thing computational, you use essentially a fixed point engine, right? A more or less sophisticated fixed point engine. And it seems to me that this is the case not only with the data flow analysis, but also with the other two things that you presented. And that was my next question. So what is the common thing?
Okay, should I answer? I mean, two things. Yeah, I mean, I know when you heard first about data flow as model checking, you said, oh, it's clear, it's all fixed points. I remember that. And my talk was essentially directly addressed to you because it says, this is not the point. And the point is, it's a new language. It's a mindset. If you want to, the examples I do, the properties I'm looking at, they are no branching properties. I'm thinking in terms of path. And many of the things in program analysis are done in path. There is no property. I mean, if you have non-deterministic systems, sometimes you want to explicitly speak about branching. I don't want to speak. I don't know any of the data flows properties. I never came across a property in static analysis where I would have liked really from the expressive power branching time logic. You are right. The efficiency of branching time logic is much easier because fixed point computation and branching time logic are very close. And LTL is much more expensive, is in principle exponentially more expensive in principle. And so you do that with automata theoretic methods. But from the DSL perspective, first, this does not matter at all. It's how do I think? I just think in terms of path. The next thing is, what is the right code or algorithm generator? The good thing is, the stuff we use typically, the LTL properties we checked, are all properties which can also be expressed in branching time logic. So it doesn't matter. So you can translate them in branching time logic and solve them indeed with fixed points. Because you can translate a lot of stuff, even LTL, into new calculus. Then you put it into a branching framework, but actually this is also an exponential gap, but luckily the properties we look at are not kind of exploiting this gap. And but the thinking, I mean, I used originally CTL or mu calculus in 1990 because I came from Edinburgh, I came from the people with biosimulation, I came from the branching world. And I think in retrospect, if I would have known, today I wouldn't use branching time logic. I would use LTL because this is the essential from the mindset, the right context. This is the language I want to think in when I specify those properties.
Yeah. Dave, what are you saying to this?
I don't have anything to add there. I think Bernhard's right. My software engineering friends say that software engineers think in terms of paths. And Bernhard is right. If they can specify what they want to say and what looks like LTL, but then you can recode it in CTL and compute it more efficiently, more power to you. You know, at the time, I was just taken back 20 years ago with the strong coincidence between branching time logic and data flow analysis. But that's just the starting point for all of this. And it makes for a great starting point for educating students as well. But yeah, Andreas, I think you're right to think about how this game might have been played if we didn't start with branching time logic. In the end,
Can I add something. You all know in algorithms, you have the mean overall path and the maximum fixed point solutions, yeah? Okay, the one is branching time, the other one is linear time, if you like. We know that branching time is indeed more efficient. And the idea, for example, to express languages, this is the big thing which people did in theoretical computer science, expressing languages and structures which are deterministic and branching time. And then you get very efficient algorithms. And if you would do it otherwise, it would be very expensive. So one thing is, if you look at the whole perspective of how you solve problems, and you look at the algorithms back in the 80s or 90s, and you look at the branching time model checking, then this is a perfect match. This is what you also, I think, feel. It's a perfect match. And in fact, I made data flow analysis, I made it with fixed point, and I saw that technical match. And I always was, I mean, there was always these, let's say, these fight between America and Europe. So the Europeans were more branching time, the Americans were linear time, the Europeans were more label transition systems, the Americans were more cryptic structures. So there was this fight, which at the meantime, people are much more relaxed about it. But at that time, there was religion, okay? My impression is, I mean, from now, 30 years later, it's actually 30 years later, the right framework is linear time logic in this case, because I want to think in the mindset fashion. The mindset for specification is linear time. And this is what Dave just said. This has nothing to do how to translate this stuff into solving algorithms. I mean, in particular, I mean, the larger the gap, the more powerful your framework. If you can efficiently solve something which is conceptually in the worst case very bad, that's of course wonderful. But thinking in terms of branching, if you don't have branching in these properties, if you really think about the properties, in this case, down safety and so on are clearly linear time properties. And think about it. I'm actually looking for properties where I really want branching. Yeah, I was really searching for it. Which kind of property is there where linear time property, linear time temporal logic is not sufficient? And after 30 years, okay, I must admit, in the last years, I'm not only just working on that, but my impression is that linear time is conceptually, from the specification perspective, simpler, because branching is, yeah, it's much more how, it's much more on the implementation side. This is my my impression here, and I agree. I mean, we use a lot of fixed points, and okay, if you go to via the mu calculus is of course checking is of course just iteration is just fixed points, but I don't want to think like it. Think of you would like to specify all your stuff in the mu calculus. It's not easy, and in these other languages, much simpler. I was, in fact, a bit frustrated that I took, at that time, the branching time logic. On the other hand side, for example, in this last part of my talk with the languages, the meta model checking, the bad story is, yeah, this stuff can only be done sufficiently, or our algorithms can only deal with branching time efficiently. Their linear time for context-free systems, I think it is still decidable, but it is very far up in the as far away, yeah. And but it is very efficient to make branching time checking of procedural structures. So one has always to bargain. And actually, in our tools, in our frameworks, we always love properties which are both, which you can express simply both in branching and in also. There's a lot of properties which you can express there. I remember there's other things which we discussed upon, you know, the Ringberg, yeah, where we spoke about liveness. Also, liveness is something very well supported also by linear time logic. To some extent, is it more, I would say it's, even though you have it in both cases, but these like fairness and similar things are typical things which we explain well in linear time logic. But we are very happy if we go back to simpler settings. Dave told me, or said it just, I mean, perhaps it's age, I like simple stuff. So rather than liveness, I like this poor man's liveness. It has to happen before something else happens. It has to happen before it terminates. it's much simpler. This is a safety property, even though I call it poor man's liveness. So in a sense, these kind of simple structures are the ones which we try to employ, because my experience is making it difficult and complicated is not difficult. It's always important to keep the complexity down.
No, I guess I was more asking in the direction, LTL for me is really about fairness, right? And as soon as, I mean, immediately when you talk about liveness, immediately you get fairness into the play. And it seems to me that you don't need that expressiveness of LTL. We don't need to express fairness constraints.
No.
Yeah. And so this is why you are in a fragment of LTL for which you have direct translations to fixed point expressions. And so for these fixed point expressions, you have your machinery. And so this was my second part. I mean, the secret of all this is that in the back you have a fixed point engine, right? I mean, it's the same for BNF and SOS. You have fixed point definitions and...
From the practical perspective, of course, you want to get a solution out of a specification. If you are just happy as a theoretician to specify the problem, yeah, let's say for partial redundancy elimination, then you don't worry first about how to get the stuff on the street. You just think how to precisely specify the stuff. And what my mindset idea is, I would like to have the simplest conceptual framework in which I can express those properties. It's not about...
Yes, but if you don't have a translation into a fixed point engine, then you are stuck, right? Isn't that true? If you don't have the translation into a fixed point expression.
I would like to, the point is, I would like to separate, I mean the separation, what and how. If I don't have the fixed point translation, I could always employ linear time model checking. Of course, it's more expensive, I'm not stuck. But then it hurts. Why not taking automata theoretic method? I could do that. At the moment, first, I mean, the problem was with partial redundancy elimination, is it possible at all? Or is it correct at all? And these specifications are very natural in the linear time setting, and they are simpler. I mean, the formula, at the beginning, I was fiddling along a lot with stuff because the representation was not nice. I mean, because the language was not nice. The question is, what are the structures you work on? And if you deal with the right of program structure and the right kind of languages, then you get this very simple scenario. If you read my original paper, things were still much more complicated because I didn't know the right mindset to really solve the problem without anything around it. So I think you see more and more that stuff you were worrying about kind of disappears when you think about it. And the point is, okay, if you want to do it, I mean, this is code generation of you, like this is a different problem to get from the what description to the how description. Sure, this can be more or less difficult. And for branching time logic, it is very direct. If you take something, if you say, I mean, if I have the same property, I can express it semantically equivalently in both logics. Yeah. Still, I want to think in the linear time logic because this doesn't speak about detail, which I'm not interested in. I don't want to think about stuff which I'm not interested in. Branching structure doesn't interest a guy who, this is what Dave said, we think about runs. On each run it happens, on each, and then it's linear time.
Yeah. No, I'm a big fan of LTL, and I guess that Dave talked about CTL because he was visiting Ed Clark, right? And so you were automatically...
That's how it started, that's right.
Yeah. Yeah, we always had this discussion, is model checking, what is model checking? And I said, model checking is just fixed point computation. But I no longer agree, by the way.
But Andreas, isn't that the same thing as saying it's computation? It's universal computation. It was like, I don't know, 2-register machine. That's it's just you go a little bit back and forth and then you iterate. So it's just fixed point computation.
Yeah.
I mean, there's fixed point computation, there's fixed point computation. There's different kinds, and and also different complexity classes of them.
Completion, and this is why all the semantics are based on fixed point definitions, I guess. Yeah.
But sometimes if you want to think about semantics, at least from a user level perspective, you don't necessarily want to think about the fixed point, but you want to think
I agree. Yeah.
And this is what I mean with mindset.
No, I agree.
Thank you, and I think Andreas, you got your answer. Why it wasn't quite coincidental that your question didn't make it in the original session. I think it warranted a longer time, more time than we had at the time presentations ended, which was actually at 5 p.m. Yeah. Great. I'll just leave you to your own devices for a little while. See you in not so long.
Okay.
But Fritz, you are still. Oh, he's still recording.
I think he is.
Okay,
yes.
sorry, I'm still recording everything because, as it turns out, hi everybody in YouTube. There's 5 people. It's because it turns out it's a lot easier to post-edit things on a single stream and actually also do the editing on YouTube. That requires actually some setup after that again. So,
actually,
I thought actually since this discussion was public, I mean here, so I thought it was great that other people could participate.
But
listen.
You are serious that only 5 people are listening on YouTube?
Well, we didn't really on this channel, because we didn't really have time to. This was set up just before the first day. Didn't have time to promote it to anything. So sorry about that. But it will be available afterwards.
You find it when you Google VMCAI 2021.
Yeah, but nobody knows what to Google for right now because we didn't sort of promote it or announce it anywhere. But the key thing is that you can't on YouTube. You can just listen, right? So, they will also be able to do that. People will also be able to do that afterwards, So when it's recorded and still there.
So you see, I'm watching it on YouTube.
Ah, me too, actually. Yes. With stereo vision, it's 20 seconds delayed. Yeah.
I can walk. It's delayed. Yeah.
Yeah.
You always see the transparency a little later. So that's another example of recursion, right?
Yeah, with a temporal fractal structure. Okay, so yeah. Okay, I think I'll see you in a little while.
Okay.
Yeah. So the next talk is by Tanya, right?
I'd be very surprised if it were. So I think the next talk is by Michel Alouf, but I might be off.
Ah, okay.
I don't know. It might be, but then I'm in the wrong place.
No, Roderick, you're in the right place because you're going to be the session chair. So
yeah, exactly.
I'm glad you're here.
Yeah, this is what made me worried.
It is Michel, yes.
An hour ago or so. That would have been bad.
No, Tanya's talk is in the second session. Within the session, we had to split. So yes.
Okay.
And I think
Roderick, could you please remind everybody just at the beginning, just to fill out the form? Sorry, fill out the 2 polls on Clowder. That's
there's 2. Okay.
Well, there's 2. There's a first one and there's a second one. So yes, thank you.
I saw one. Okay, everybody, please fill out the poll. Okay.
In 4 minutes or so. Yeah, thank you.
Yeah. I'll say it again. But where do I find the poll? Because I just filled out one. I don't see the other one.
So I see them both on the chat.
Okay.
But actually, it doesn't let me choose anything for the second one.
Maybe that's good. So maybe also what we can check is, Michelle, are you there? Can we see if your video and audio work?
Yeah, hold on.
She answered.
Ah, so we can see you. Well,
Can't hear me?
a little bit quiet, but we can hear you.
Okay, I mean, I've been trying to fix this headset all day.
No, it's good. It's good. It'll work. Can you share your screen? So I can see from
Yes. Can you see the screen?
Yeah, that's great. Perfect. Okay, so it's 6, at least it's in my time zone. So welcome very much everybody to the next session. It's called Case Studies. I was asked for 3 things. First of all, if you're in Clouder, and you should be, then there are 2 polls. If you could fill them out, that would help us a lot. Second, if you could turn on your camera, that would be really nice. It really helps the speakers if they see that somebody is listening and not just pretending to be here. And I think you've all done this, but if you can turn off your microphones, that would also be helpful. At the end of each talk, as for all of the talks here, you can ask your questions in audio. You can just unmute your microphone. We may have some discussions. You can also ask in text on Clouder, and I'll see your questions and then relay them. Okay, so having said that, I think we can get started. So our first talk is titled Formal Semantics and Verification of Network-Based Biocomputation Circuits. And it will be held by Michel Alouf Medina from Bar-Ilan University. So Michel, please go ahead.
Thanks for the introduction. This work was a joint work with Till Korten, Avram Raviv, Dan Nicolas Jr. and Hillel Kugler. That's on the semantics for the network-based, the NBC circuits, network-based biocomputation circuits. So as you can see a diagram, an example over here of what these circuits look like in real life. So these devices are being manufactured as part of the European Commission's Bio4Comp project. So network-based biocomputation circuits. NBC circuits are molecular networks that encode combinatorial problems. So they utilize the parallelism of the biological agents to calculate the solutions to these problems in speedier, using speedier computation, low energy consumption, and they allow for the possibility to interface with medical applications. So the answer to the combinatorial problems are deduced by looking at the outputs of the network. So as seen at the bottom of the video on the right. So the biological agents can also be tagged as part of an error detection system or as part of the actual computation itself. So we looked at the logical design of these circuits and ran verification on their the formal correctness of their structures. So we looked at 3 NP-complete problems, the first of which is the subset sum problem. So we're given a set S and some target value K, and we want to see if we can sum a subset of the elements from set S to reach value K. So the network example you can see here on the right of the overall network structure. It's built up of 2 types of junctions. So we have the pass junctions, which maintain direction of the computational agents in the network. So they move in a downwards or diagonal direction in the network on the right. And split junctions, which allow the agents to take either direction at approximately 50% probability. So we have, in the example, we've encoded the subset sum problem for the set of elements 2, 5, and 9. So each split row is at the relevant index for each element in the set. And we can see the yellow path, for example, we took sets, the elements 2 and 9 from the set to reach a sum of 11. So you see the use of the diagonal implies addition of the element into the sum. So we formalized the problem as a transition system so that we could use model checking. In our case, we used the new SMV model checker. So we construct the network using variables to describe the position of the agent in the network, what type of junction it's in, what direction it's moving. We added an additional tag element it's an optional element for tracking the locations where diagonal directions were taken. So we used 2 model types using 2 different specifications. The first specification type, we checked the overall reachability of a specific output or the lack of the reachability of that output. And the second specification type, so the type 2 specification checks the reachability of a pre-calculated set of valid sums, and it checks the unreachability of a pre-calculated set of invalid sums. So we use these 2 models. We checked using number of different methods, so the 2 specification types, the different types of CTL versus LTL, the networks with tags and without tags, and the 2 specifications as one opposed to the other. So we got the expected results for all the networks. The outputs all were as expected. So the second network type that we looked at is the exact cover, which is very similar to the subset sum network because we defined it. It was defined using a reduction to the subset sum by making a binary conversion of the universe in sets and encoding the problem in that manner. So each universe from the exact cover is encoded as a binary number of all ones, and each of the subsets is encoded as a binary number of the existent elements from the universe at the relevant indices. So the question is there a union of non-disjoint sets where we reach the sum of the universe? So this using this conversion, we see that the universe in our sample here, where the universe is 1 through 4, it translates to a 4-digit binary number with all ones, so it's a decimal value of 15. We see that the set 1, for example, has only the element 2, and so it has a 1 in the 2 position, and so it translates to a decimal value of 2. So the encoding goes from a least significant bit being the 1 to the most significant bit being the 4. So using this conversion, we can see that there's, in the example network, there are 2 paths to a valid output of the exact cover. So there's 2 ways to get an exact cover. There's an additional junction type that was added to this network that prevents union of non-disjoint sets, which is the minor difference from the subset sum network. So this is the orange junction in the diagram. So the pink path, for example, it takes sets 1, 2, and 3, and then it is forced to take the downwards direction at set 4 because it is not disjoint with sets 1 and 2. So we again formalized the network using new SMV language and described the network using the same variables. There's just the addition of the force down junction in the junction types. The specification type used is the same as the initial specification, the specification type 1 from the subset sum problem. In this case, where we actually know what the value of k is, we're not checking for each individual k. We know that k is 15 in this case, in the example for the universe, and that's the only value we're interested in. So up until this point, all of our designs were considered correct. All of our results came out showing that the results we get are as expected. So we decided to look at what happens if we deliberately enter errors into the network. So we have defined 3 types of errors. So if a pass junction behaves as a split junction, or a pass junction forces one direction, or if a split junction behaves where it forces a single direction as well. So this is in the specifically for the subset sum problem. In the exact cover problem, we have another question of, do the force down junctions behave as expected? Or did we make a mistake and maybe treat them as all split junctions? So it's a mistake in the translation. So we can see that in some cases, we using the second specification type on subset sum, we can see the change in the output from the valid networks as compared to the faulty networks. And in the exact cover, we can see that the change of the behavior of the force down junctions leads to reaching exact covers when there should not be any exact covers. So the third network that we looked at was for the satisfiability problem. So does there exist an assignment for the Boolean formula so that the formula evaluates true? So the network structure here is considerably different than that of the subset sum and the exact cover problems. We require the use of tagging in this case as part of the computation. Junctions are designed for the variables and clauses, where a left path from a variable is a true assignment and a right path is a false assignment. At each clause junction, a tag is received to mark that that clause has been satisfied. And once agents reach the output, we want to see that all tags are present to consider the problem satisfiable. So we formalized this network as well, this time using variable and clause positioning, the direction assignment, the junction type, and the movement direction. We used a tag as a counter to count the number of times a clause is satisfied. So this counter, we set it from 0 to 3. So we're using the 3 sat. So the specification in this case will check that the tags are greater than 0 at every instance of tag. So there's a tag for each clause of the problem. So we check that every single tag is present by checking that it's been satisfied at least once. So we ran the networks through an SMV again. We had some benchmarks over here from the random. We have random 3CNF formulas that we ran this on. So we used variably ordering by the first appearance of a clause in the network. This in some cases helped and in some cases didn't with the runtimes. So this work it sits in a broader concept of designing biological computation devices. So there's other work in this field that's further mentioned in the proceedings. So overall, what we've done is we've provided formal semantics for these designs that were manufactured in Bio4Comp. We've tested the error handling of these designs, the possibilities for error handling. In the future, we look to improve the scalability and of the verification, and to look at a probabilistic verification. So because the agent behavior doesn't is not always correct. So we want to include those error rates as part of our verification. So for this, we already have some preliminary results. So that we look also into the future to integrate this with the simulation and design tools, and see for further applications for these circuits, what they can be used for. So thank you for listening.
Okay, thank you very much, Michelle. Are there any questions? So maybe I can start. So I wanted to ask about the probabilistic aspect, because you mentioned this in the first slide. And then for the problems that you presented, it didn't seem to be relevant at all. So can you say more about that?
So the way the agents run through the network, there's a probability of error at each junction type. So I mean, split junctions are one thing, but pass junctions are the main part of where we concentrate on this, of the possibility of an error of a junction, of an agent maybe taking a different direction than what was intended. And so we are looking into now the probabilities, what are the probabilities of this happening, and how much can we handle, and such.
That's interesting. So what I actually noticed was that your split nodes you defined them as probabilistic nodes and not as non-deterministic nodes. Is this relevant, or?
They're technically they're supposed to be non-deterministic. It's the agents are supposed to be able to choose non-deterministically to take either path. It's just my manner of speaking.
Okay, yeah, thank you.
So,
any other questions? So if not, then thank you very much again, Michelle, for the very interesting talk. So then we'll move on to the second talk of the session, which is called Netter, Probabilistic Stateful Network Models. And this talk will be given by Han Zhang from CMU. So go ahead, Han.
Is everything all right?
Excellent.
Cool. Hi, my name is Han, and today I'm presenting Netter, a probabilistic stateful network modeling language. This project is a collaboration with my colleagues at Carnegie Mellon University. In recent years, there have been a lot of interest in building automated tools for network verification. Here is an example of a simple network topology. This shows the connection relationship between hosts in the network. Given a particular topology, we want to analyze this network and be able to answer questions like, can every host be reached when some link fails? Or what is the average latency between two hosts in the network? Sorry. Some of the qualitative questions, such as reachability and freedom of routing loops, have been more well studied by recent works. On the other hand, many of the quantitative ones receive less attention but remain challenging to answer. These properties are often probabilistic. Certain analysis approaches, such as simulation, could quickly run into issues due to the complex models and large number of possible executions. Instead, researchers have turned to tools like probabilistic model checking to tackle these challenges. Several prior works already proposed languages to encode network programs in order to conduct model checking. Bayonet and ProbNetCat are two examples that are most relevant to this kind of analysis. Bayonet proposes a flexible language to capture complex models, incorporating router internal states, queue-length, and even considered packet ordering. However, the expressiveness comes at the expense of limited scalability. According to their evaluation, their tools can only support tens of nodes and up to 20 packets at a time. On the other hand, ProbNetCat introduces a more restrictive language design, skipping support for many router states and packet interactions. As a result, they can scale up to networks with thousands of nodes. The goal of our project Netter is to provide a middle ground between expressiveness and scalability in the language design. One key insight in Netter is that we use a flow-level abstraction to model network programs, while prior works model networks based on the forwarding behavior of individual packets. A network flow summarizes high-level characteristics for the traffic between a particular source and destination pair. Individual packets from the same flow follow the same flow path, and they contribute to the overall statistics such as flow duration and flow size. We want to focus on analyzing network behaviors in the long run and are interested in the interactions between different sources of traffic. Therefore, taking a flow-level abstraction greatly improves Netter's scalability and enables the modeling of more stateful programs. Here is the workflow of analyzing Netter programs. Netter is a simple imperative language. We implement it as a Haskell-based domain-specific language. End users write their own network programs in this high-level DSL. Their Netter program includes the model code and custom performance metrics. For example, here the performance metric is how to calculate the network latency between hosts. Next, the Netter compiler takes the model input and produces a discrete time Markov chain model. We apply several optimization strategies in the compiler, including aggressive inlining and dead store elimination, to produce an efficient and succinct Markov model. We also prove the correctness of these optimizations with our Coq formalization. As the final step, we run the Markov chain code with standard off-the-shelf model checker. For our prototype, we use a high-performance checker called Storm as the default backend. In addition to the model code, users also need to provide the property they want to check for. For example, here, the query is how to check the expected latency. The model checker will then compute the answers to the query. We use Netter to encode 4 different network programs as case studies. These programs demonstrate Netter's expressiveness and comparable scalability with other tools. I will briefly go over 2 cases today due to time constraint. Please check out our paper and the open source artifacts for more details on all of our case studies. Load balancers are often used to distribute workloads across a pool of servers. When a new job arrives, the load balancer decides which worker should process it and then forward the request. Certain load balancing algorithms are stateless and relatively simple. One example is to randomly select servers through coin flips. Prior work like Bayonet and PropNetHat both can model such an algorithm. However, there are many stateful load balancing algorithms used in the real-world system. Depending on the workload, they can often outperform the stateless alternatives. Trying to encode these algorithms with prior tools is a challenging task. In some cases, we can't model the rich state information, while in others, we can't analyze the long-term routing performance in order to compute the server utilization. In comparison, it is much easier to do so using Netter. Take this example, random choice of 2 as an example. When a new flow arrives, the load balancer picks 2 servers from its pool, compares their current workload, and then forward the traffic. This algorithm is both probabilistic and stateful. Here, we show a snippet of the corresponding Netter code to model the random choice and comparison. Since Netter is based on Haskell, end users are free to use any Haskell types and operations to encode the algorithm. During compilation, the Netter compiler does the heavy lifting to decide where and how to store internal state variables in the final Markov chain model code. In total, we use Netter to implement 3 load balancers and compare their performance in terms of allocation fairness and the expected flow loss. We found that random choice of 2 often performs better than round robin, but we do find a few corner cases that show the other way. Now, let's move on to the next case study. Another example we looked at is how different routing algorithms for DDoS mitigation could affect individual hosts' throughput. Quantitative network analysis can provide useful information here. Network engineers can check the desired property host before deploying any new algorithm into production. Here is an example topology from our paper. We have several clients on the left trying to communicate with the server on the right. Suppose the first client is malicious. The attacker can flood their link to the router, causing degraded performance for the victim. In response, the victim can switch to its backup link with another router. However, the actual performance gains depend heavily on the specific routing algorithm running on each node. One property we would like to check for is what's the expected bandwidth allocated for the victim flow, subject to the router's algorithm and the victim's link of choice. There are a number of challenges in implementing this example. First of all, depending on the application they're running, clients are modeled as different types of flows. We can model fixed bandwidth flow as constants or statistical samples from a particular distribution. However, for dynamic bandwidth flows, we have to use a two-step flow allocation procedure. In order to achieve that, we have to store a lookup table to keep track of all flow allocation status and each router's free bandwidth at every step. This creates a large number of states for the model. Thanks to the optimization in the compiler and the high-performance model checker backend, we were able to generate a modest-sized model code and analyze it relatively easily. We implemented 3 routing algorithms in Netter and compared their analysis results of expected bandwidth for a particular victim flow. The first algorithm let routers drop packets randomly during congestion. In this case, switching to backup link greatly improved the victim's bandwidth. The next algorithm categorizes network traffic into different types and gives different priorities. Assuming the routers only give a low priority for victim flows, the victim sees a modest performance improvement after the switch. In the last case, we implemented a collaborative DDoS mitigation algorithm called CODEF. They assign unique labels for each source destination pair. Therefore, the victim is guaranteed with a fair share even if they stay on the primary link. Our analysis results are in line with the original CODEF paper and its simulation results. In summary, we proposed Netter, a probabilistic network modeling language. We implemented a Netter compiler and explored 4 case studies for expressiveness and scalability. For future work, we would like to apply more optimizations to tackle scalability issues. For example, we can integrate symbolic analysis techniques that do not require explicitly enumerating all the network states. We would like to include more security-focused network programs as case studies to extend the language's expressiveness and coverage. Finally, the code for Netter is open source. You can check out the GitHub link to use the Netter compiler and take a look at our evaluation artifacts to see the models used for the case studies. Thank you.
Thank you very much, Sean. Are there any questions? So let me start. You talked about a few different network setups that you could do to treat problems, right? So my question is if you can automate that. So could you like change the tool where you could say, well, can you find a simple change to the network such that this property is fulfilled afterwards?
So I think you need a fixed topology in order to write the model code. I don't think it will be easy to switch the other way to do some constraint solving or looking for some property host and ask it to find out the topology or find out the configuration. It's mostly the goal here is to model different like software components, like algorithms, routing algorithms, or prioritizations, and you just fix the topology and then you fit in different things and to quantitatively get an analysis result before putting into production.
Mm-hmm.
Yeah.
Okay, thank you. Yeah, makes sense. Any other questions?
What is the difference between your Netter and Prism probabilistic model checker?
Prism and probabilistic model checker is our backend. So we are, let me go back to the workflow part. So the goal of Netter is for end users to write their program in a high level language, and then we can compile that into a model that complies with Prism's language syntax, and then you can run Prism, or an alternative is Storm. So you can simply replace this Storm model checker with a Prism model checker. That's the same.
Thanks.
So what is the typical size you have for the Markov chain model? And for Storm and Prism, both tools to do model checking, you have to bound your variables in your model. Are those bounds provided by your Netter compiler as well? Thank you.
Yeah. That's a good question. So it really depends on the complexity of your input model. For example, if you want, in our evaluation, in the DDoS example, we have a 10 nodes topology. So we have 10 individual components we want to model. But and we were able to do that in, I could be wrong, but finish in seconds. But if you just directly scale up to like 10,000 nodes, that will explode the model size. So it depends on the complexity of your input. And we also have a performance evaluation for a simple network topology to show that here's the number of switches and the corresponding model checking time. Yeah, you're right that you have to be very careful about the model size and keep it reasonable in order to conduct model checking.
Thank you.
Okay, are there any further questions? So if not, then thank you again very much, Han. Thanks to both speakers for their very interesting talks. If I'm looking at the schedule correctly, then we have a break of 1 hour now. So the conference resumes at 7:30 CET with a session on decision procedures, and you can stay online for the.
Moderate?
Don't have a break.
Yeah, sorry, thank you. Please correct me.
Yeah, so we continue immediately. We just switch sessions.
Right.
Yes.
I apologize. Thank you.
Thank you.
Okay. Hi, everyone. My name's Alex Summers. I'm happy to introduce this session of 4 talks. And the first talk will be by Martin Bromberger, Alberto Fiori, and Christoph Weidenbach. I think Martin is here.
Hi.
And I'll leave him the honor of reading out the title. So please go ahead.
Okay. Good evening. So my name is Martin Bromberger, and this talk is about deciding the Werner-Schonfinkel fragment over bounded difference constraint by simple clause learning over theories. Now, one of the main motivations for our work was the Dieselgate scandal. As you might remember, several car companies decided to cheat on the emission tests. For instance, several companies began turning down their pollution control when the outside temperature dropped below the temperature inside a testing facility. These so-called defeat devices were all hidden in the software of the car's engine control unit and are very difficult to detect through hardware tests. In our opinion, it might be better to directly verify the correctness of this software. A major advantage of this setting is that the software in such a control unit is well structured and not very complex. In fact, we can model the engine control unit and the properties we want to verify in a very nice fragment over first-order logic, the pure Werner-Schönwinkel fragment over theories. The pure Werner-Schönwinkel fragment contains all formulas that have only universally quantified variables and that contain no function or constant symbols. Without loss of generality, we can also assume that these formulas have all been preprocessed into a CNF form, so we just have a conjunction of clauses. And the typical goal for this fragment is to find an interpretation for the sorts and predicates that is valid. An interpretation specifies the argument values that can instantiate the variables and under which arguments the predicates evaluate to true. And an interpretation is valid if every clause evaluates to true under each variable assignment. However, for our purposes, we actually extend each foreground clause by a so-called background theory constraint. The background theory constraint is a conjunction of theory atoms that removes for each clause some of the variable assignments that we have to check for validity. In fact, we only have to consider those assignments that also satisfy the theory constraint of the clause. Note that in contrast to the foreground clause, the background theory constraint is built from a collection of symbols for which we already know the interpretation. For instance, we typically need an arithmetic background theory for our purposes, and the symbols have the semantics you know from math, like plus, minus, or greater and equal. This also means that we have to slightly adjust our fragment restrictions to forbid only constants and functions that are uninterpreted. Now the question is, with which theory can we now model our engine control units in this fragment? And at least for our paper, the theory of bounded difference constraints, because the majority of the engine control unit can actually be specified with it, and because it's still decidable. And most extensions of it are not, or at least we would need some further restrictions to our foreground part. Now the theory of bounded difference constraint is also relatively easy to define because we only have 3 types of atoms. So we have on the one hand variable bounds where we compare a variable with an integer value. We have 2 variable comparisons where we compare 2 variables with each other. And we have difference constraints where we compare the difference of 2 variables with an integer value. There's, however, one further restriction. We only allow difference constraints in a clause C if its variables are also bounded in the clause. This means there must be a lower and an upper bound for each variable. As a result of this restriction, this standalone difference constraint here is actually not allowed. But together with the following bounds for x and y, it would be allowed again. Now that we have defined the logical fragment we need for the verification of an ECU, we can also define what we want from a solver for this fragment. So first of all, we want some kind of completeness guarantees. Because if we always return unknown, then this isn't really fair, and we wouldn't really get this through as an official certification method. Or at least the car companies would complain that our system isn't fair enough. Next, we want some explicit certificates and especially explicit interpretations. We need them because the end users of our system will be automotive engineers and not logicians. And they would definitely prefer an interpretation in the form of a mathematical function that can be visualized as a graph or diagram. And last but not least, the solver needs to be efficient in practice, because completeness does not help us if we need decades to verify the software for the newest car model. And unfortunately, we could not find any existing solver that can satisfy all of these requirements. So we had to define a new calculus that does satisfy these requirements, which is also the contribution I want to present today. Now the calculus is called simple clause learning over theories, or short SCLT. It takes as input a set of clauses over our chosen fragment, and during our search we use a state consisting of the following additional elements. First of all, we define a set of Resch constants B. Based on these constants, we build a ground partial model assumption called the trail that can be seen as a set of sample points for our final interpretation. the techniques we use to build this trail are inspired by subsolving. Essentially decisions and propagations performed on ground versions of our clauses based on the set of constants B. Since decisions are just guesses, it can happen that we build a trail that conflicts with one of our ground clauses. So this trail doesn't correspond to an interpretation that could validate this clause. In this case, we try to resolve the non-ground version of our conflict clause with the non-ground clause we use for propagation. And this is done via hierarchic resolution. And the result will be a new non-ground clause that could have been propagated earlier and would have prevented the conflict. Now we learn this clause, backtrack to the right position on our trail, and propagate with this clause instead. And this way we block this conflicting trail, and hopefully the clause will also help us to block further conflicting trails in the future. At some point in our search, we also come to one of three possible results. So either we learn the empty clause, which proves that there is no valid interpretation, or we find a trail that corresponds to a valid interpretation. I will show on the next slide how we can actually detect this. Or we notice that we need more sample points, which means we need more constants to reach one of the previous two results. In this case, we extend our set of constants and restart our search. Now, as mentioned before, the trail can be seen as a set of sample points for our final interpretation. We can detect a valid interpretation based on these sample points because Werner-Schönfinkel over boundary difference constraint has a finite model property that looks as follows. If we have a valid interpretation for a formula, then there also exists a valid interpretation for which we can divide the argument space of each predicate into a finite set of regions, and the predicate has the same truth value for all argument tuples that belong to the same region. Now the regions for binary predicates and a formula without any variable bounds or difference constraint looks as follows. One region stands for all equivalent argument pairs. One region stands for all argument pairs where the first argument is smaller than the second. And one region stands for all argument pairs where the first argument is larger than the second. Based on these regions, a trail corresponds to a valid model if it fulfills the following properties. So first of all, the conjunction of the trail litters must be satisfiable. This is actually guaranteed by the way we built this trail in our calculus. Next, the trail must satisfy all ground clauses derived from our clause set over our set of constants. This again will be satisfied by our calculus, so we don't really have to go into more details. More interesting condition is that we need at least one ground instance of our predicate for each of our regions. And last but not least, if we have multiple instances for a region, then all instances must be either positive, so true, or negative, so false. Now in the example here above, we have just one constant. As I mentioned before, these first two properties, conditions are simply true by the way we compute our trail here. But because we only have one constant, we also only have one sample point for the case that our two arguments are equivalent. So our third condition is not satisfied. Coincidentally, our fourth condition is because we only have one sample point. Now, as a result of this, we would decide to extend our set of constants to two constants. And in this case, we would find a new trail, and this trail actually has sample points for all of our three regions. So the third condition is now also satisfied. And we have for one region two sample points, so P of A and A, and P of B, comma B. But both of these sample points are negative or false. So we are still uniform over this region. So our fourth condition is also satisfied. And this means this trail here actually corresponds to a valid interpretation. And the interpretation actually looks as follows. So P is true if our first argument is greater than our second argument. And we would then extract this argument and return this to the end user. Now, as a conclusion to my talk, I will discuss again the requirements for our solver and explain in which way SCLT fulfills them. So first of all, SCLT is refutationally complete, as long as the theory is decidable. This means we always find a proof of unsatisfiability. Secondly, SCLT is complete for the Berner-Schönwinkel fragment of a bounded difference constraint due to its extraction criteria. And for this fragment, we also always find an explicit interpretation if our formula is satisfiable. So completeness and explicit certificates are both fulfilled. But with regards to efficiency, I cannot yet present any conclusive results because we have just started working on a prototype of SCLT. However, SCLT already exhibits some nice properties that are quite promising. So first of all, SCLT, unlike other solvers based on hierarchical resolution, is guided by a partial model instead of static order. And we hope that this will lead to a better interaction between foreground and background reasoning, like for instance in SMT solvers. Now, unlike, for instance, SMT solvers that use instantiation to handle universally quantified variables, SCLT is also able to learn non-ground clauses, which are much stronger effects than the ground clauses learned in SMT solving.
It would be a great place to wrap up if you're close, Martin.
Yes, I'm close. And last but not least, SCLT provides non-redundancy guarantees for each learn clause. This means that we do not have to spend the majority of our time on redundancy elimination, as is often the case in superposition-based solvers. And yeah, for future work, as mentioned before, we want to implement SCLT and hopefully find some new extraction criteria and some new completeness results for other theories. And hopefully we can then verify the full engine control units. And so thanks for your attention. And if you have questions, then please ask them.
Great, thank you for the talk. So who has questions?
I have a question. This is Cesare Tonelli, University of Iowa.
Hi.
Hi, Martin. I had a quick question about this. Could you say again, what are the properties of the theory T that will make the framework work here?
So in a sense, we need a final model criteria. So we must be able to have an interpretation that can be divided into connected regions, and there are only finitely many of these regions.
Is there a way to characterize this more operationally? I mean, how do I recognize a theory like that?
So this is actually something we're currently working on. So I have an idea how we can do this, but it's not yet guaranteed if this is actually true. So I believe if we can formulate the interpretation as just a formula over our theory, then it has this final, then this interpretation is final. So if we have such an interpretation, then it would work.
Okay.
So we might even be able to do this for other theories as long as we restrict ourselves to those formulas that have these finite interpretations.
All right, sounds good. Thank you.
If there's a very quick question, we could squeeze one in. Otherwise, thanks, Martin. Thanks for the talk. So we'll move on to the next. And the next is work by Jochen Hoenicke and Tanja Schindler. And Tanja is here, I think.
Yes, I'm here. Thanks.
So please go ahead.
Can everybody see my screen?
I can see.
Okay, great. Yeah, so now we're back at SMT solvers, and I'm presenting work on incremental search for conflict and unit instances of quantified formulas with e-matching, which is joint work with Jochen Hoenicke. In the context of quantified problems, the common approach of SMT solvers is, as Martin already said, to subdivide the formula into a ground part, which is solved by the ground SMT solver, and the quantified part handled by a quantifier module, which adds instances to the ground solver depending on the partial model or other information it has from the ground solver. And the goal here is to add instances that allow the ground solver to derive unsatisfiability, or in some fragments, even satisfiability. The problem is to find the right useful instances to show unsatisfiability, and there are several approaches. The most common approach is e-matching, but there are also other approaches like model-based quantifier instantiation, the DPLL gamma calculus, and conflict-based quantifier instantiation. So I first would like to show an example for a quantified problem that shows which kind of instances we would actually like to have. So on the left side, you see a formula F, a ground formula over the theory of equality and uninterpreted functions. And on the right side, you can see a quantified clause with variables x and y. So an instance that we could produce from this quantified clause would be the following. We map the variable x to A and the variable y to B and get the instance below. If we now have a closer look at the instance and the ground formula F, then we can see that they are together unsatisfiable because the first two literals in F contradict the first literal in the instance by congruence reasoning on the first argument of G. And the last literal in F is just a negation of the last literal in the instance. This will be our running example. And yeah, this the kind of instance that you can see here will be called conflicting. So our contribution is a new method to find conflicting, but also unit propagating instances of quantified formulas. Unit propagating means that the instance can lead to a propagation of a new fact about known or unknown terms. The method finds the candidate instances using incremental e-matching and evaluates the candidate instances without actually creating the instance. And we treat here the quantifier module as a theory solver in the DPLLT calculus. As you see, the work is based on e-matching, so I would like to first explain e-matching a little bit. So again, this formula from the beginning. On the right side here, you see the E-graph that is constructed from the formula. Nodes represent terms, arrows represent function argument relations, and dashed lines represent equalities that are introduced either by the literals or by congruence. And there's also a disequality edge on the right side. E-matching based instantiation works as follows. We choose a pattern, which is a term containing variables from the quantified formula. It should either contain all variables, or we can choose a multi-pattern containing all variables. And then we find an equivalent term or congruent term in the E-graph, and a substitution for which this term is congruent. So in this example, we can match the node G with the node G on the left side, for instance. Then we go down to the arguments of G. The first argument of G is an F term, which is not the case for the left G, but the argument B is in the same congruence class as an F term. So this is a valid match. Then we go down to the next argument, map X to A. And for the second argument of G, we can just map Y to B. So we get a substitution mapping X to A, Y to B, and an equivalent term G of B, comma B. And we end up with the instance that we already saw in the second slide, which is a conflicting instance. But we could also match the pattern with the term G of B, comma A, and get the substitution that maps X to A and Y to A, and get another instance. Then we would add these instances to the formula F. The formula together with the instance is unsatisfiable because C sigma with the first instance is already contradictory. Another thing that we can observe is that we found an instance that is already satisfied. The second instance is satisfied by the first literal. I marked the terms and literals that make the first literal true in this greenish color. And this can be seen in the formula, but also in the E-graph, because we found this term G of B, comma A, and we can just compare it with the term on the right side A. So the evaluation of this clause is actually possible without building the instance, because the e-matching found a congruent term, and we can just look up in the graph if the congruent term is in the same equivalence class or a disequality is set. And this is the core insight for our method. So from now on, we restrict ourselves to formulas in conjunctive normal form, where we have ground clauses and universally quantified clauses. And we also restrict this for this talk to the theory of equality. So I want to define now the kind of instances that we are looking for, conflicting and unit propagating instances. We assume that we have a partial literal assignment M and a class of literals L1 to Lm containing variables x1 to xn and a ground substitution for the variables. Then we say that an instance C sigma is conflicting if M together with the instance implies false in the theory, or equivalently if M implies that each literal is false, or each instance of a literal is false in the theory. And similarly, an instance C sigma is unit propagating if there is an I such that M implies that each literal instance is false for all literals with indices other than I. So again, back to our example. Now I chose the literal assignment that only set the first two literals to true, f of A is equal to B and G of B, comma B is equal to A. We consider again the instance that we have seen before. And now C sigma is unit propagating for M, because the first literal is falsified by M, but we don't know anything about the second literal yet. If we add the literal assignment G of B, comma A is distinct from A to M, then we get that it is conflicting. So our approach to find those conflicting and unit propagating instances consists of 3 steps. We assume that we have a quantified clause. Then for each literal in this clause, we find a substitution sigma and terms T and T prime in the E-graph such that T is congruent to the left side and T prime is congruent to the instance of the right side of the literal. So this is just E-matching with the multi-pattern P and P prime. In the second step, we evaluate each equivalent literal. So we use the equivalent terms to evaluate the literal and just look up the information in the E-graph. And in the third step, we extract the conflicting and unit propagating substitutions for C.
You want to be wrapping up in a couple of minutes, Tanya.
Yes.
Thanks.
So I want to, I would like to make an example that uses the information that we found before already. So we have this E-graph again. And in the first step, we match. So we match g of f of x comma y. We already know that we can find two congruent terms here. In the second step, we match the other literal and find the congruent term g of b comma a. So now we have two substitutions for the first literal and one substitution for the second literal. We can evaluate them, and we already know that the first literal instance is false, and the second literal instance is true, which we call irrelevant for our method. For the second literal, the instance is false. And now we just combine the lines that match to each other. So we can combine the first two lines and get an instance substitution for the clause C that maps it to false. So it's a conflicting instance. We can also combine the last line of the first table, which is a line that we introduced to also allow unit propagating substitutions, but is not used in this example. And yeah, finally, so we found this instance again, and then we can build this instance. Okay.
Would it be possible to wrap up around here?
Yeah, so I would like to say that something about completeness. So every conflict on a single clause instance can be found with e-matching. And this requires a little bit of pre-processing that we don't actually, we didn't implement all of it, but you can see the details in the paper. And we implemented it in the SMT solver SMT Interpol with two settings that find instances either eagerly before decisions of the DPLL engine or lazily after a complete ground model has been found. We complemented it with an enumerative instantiation for completeness in decidable fragments. And then we evaluated this on the SMT-comp benchmarks UF, compared it to an e-matching based instantiation within SMT Interpol and to CVC4 and C3.
Yeah, so we really should stop there. I'm sorry. Maybe you could.
Okay.
Maybe you could take a question or two if there are questions.
Okay. Thank you.
Sorry to interrupt. Thanks for the talk. Does anyone have any questions, please? I could certainly ask one. If I hope I don't miss the point, but could you compare a little bit with how this relates to kind of non-ground resolution techniques for handling quantifiers? So if you try to find instantiations this way, is there any relation?
No, I don't think so. I mean,
okay.
We are just looking for substitutions where we have equivalent terms.
Mm-hmm.
And this is determined by the partial model. And then we just evaluate these substitutions, the instances generated from these substitutions.
Okay, thank you. Are there any other questions? Okay, thank you very much for the talk. Then the third in the session is work by Tobias Paxian, Pascal Raiola, and Bernd Becker. And I think Tobias is here.
Yes, Tobias is here. And
please go ahead.
Thank you. And it's again a work from University of Freiburg and on pre-processing for weighted maxset. It's a joint work with Pascal Raiola and Bernd Becker. We faced a few scalability challenges for our own application where we had some maxset instances which had more than 1.2 million soft clauses and up to 30 million hard clauses. This is especially hard for PB-based maxset solvers, our own solver Pacus. But we could exploit the structure of these instances, which have a special weight distribution, and efficiently get a first approximation of the weight. The application is in reconfigurable scan networks, where we have confidential data module and another third-party module where the data can be shifted over. How can we resolve these security weaknesses such that this data is not shifted over the observable module? And this is translated partly into a weighted max-SAT instance. But what is SAT and max-SAT? SAT are only hard clauses. Here in this example, the first and the third clause together are contradicting the second clause, such that this problem is not satisfiable. Let's go directly to partial weighted max-SAT with soft and hard clauses. The hard clauses have to be satisfied. The soft clauses should be satisfied, as many as possible. In the case of partial weighted max-SAT, each soft clause contains an integer weight, and we try to satisfy the maximal weight combination. In this easy case here, the hard clauses are satisfied together with the first soft clause, and then the weight is maximum. Let's start with the details on how to solve this problem. There is a work already on Boolean multilevel optimization from Igelic et al. From VMCAI 2009, where he has a special weight distribution over the problem. Let's assume that each of these weights are corresponding to one soft clause. There's a great weight difference in them, such that this can be seen as two goals to satisfy. If we satisfy only the higher weights, it does not matter how the lower weights are solved afterwards. It does not influence the result. It is so if the smaller weights, the sum of the smaller weights, are smaller than the next highest weights. Then we can solve the first goal weights, pinpoint the higher weight with an encoding in CNF, and then solving the secondary goal. But this is not always possible. Attention here, this condition is met too, but there are different weights in the first goal. By solving only the first goal here, 102 could be the result in the primary goal, contradicting to all other soft clauses if this soft clause is satisfied. But the overall result could be 151, which cannot be satisfied then anymore. So we looked for rules how to generalize this, how to have rules for multiple weights in one goal. And we found out that if the sum of the weights of the second goal is less or equal than any positive difference between the sums of any two subsets of the first goal weights, then it is possible to split them. What does this mean? The sum of the secondary goal weights is 4. The weight subsets are here in black, and the sums of all these subsets is here in green. And we are looking only at these green sums and the difference of them. So 28 minus 23 bigger equal 4, and all of them are greater equal 4. So in this case, we can split the weights. By only changing 14 to 16, it is not possible to split the weights here, because for the same reason as before, if we solve the weight 16, it could contradict if we solve the first goal, having the optimal result, for example, 16, but this soft clause 16 could contradict all other soft clauses here. So, but there's a higher overall weight possible if all other soft clauses are satisfied. So this cannot be split here. It's quite inefficient to check for all weight, such weight combinations, as there are 2 to the power of n weight combinations in total. But we found a sufficient criterion with, which is the greatest common divisor. The sum of weights of the second goal is less or equal the greatest common divisor of the first goal, then we can split the weights. This actually is enough for splitting all weights in the 2017 till 2019 max-set evaluation benchmarks, which is around 5% of these benchmarks, which are splittable only with the generalized version of the Boolean multi-level optimization. The second technique we implemented is trimming the max-set instance. It excludes always unsatisfiable soft clauses and finds a solution close to the optimal fast. This combination largely reduces the encoding size for pseudo-Boolean solvers. It combines backbone computing, which finds the unsatisfiable or satisfiable core for such formula, with approximation techniques of max-set solvers. The workflow of both preprocessing techniques is we have a max-set formula, we split it into sub-goals, start with the sub-goal with the highest weights, apply trim max-set, solve the instance, add an encoding to ensure this highest found weight, go to the next highest weights, until we finally can print the result. The results for our RSN application benchmarks. We used here our Pacose 20 solver, here only with one encoding to see the pure impact of the new techniques. Without the new techniques, the yellow line can solve a bit more than 650 instances. Only with Trimaxat, a bit more than 700 instances are solved. With GBMO, around 100 additional instances are solved. And with both techniques combined, all of the 779 instances could be solved in less than 200 seconds. We compared this result with the max-set evaluation solvers of 2019. The last three solvers here are pseudo-Boolean solvers, which are told at the beginning for pseudo-Boolean solvers, these instances are especially hard to solve. Then we have here the first solver of the max-set evaluation, RC2 2018, then UWR max-set, which already solved all instances, which was the second solver of the max-set evaluation, and the third solver, MaxHS. And we could solve all instances in less than 200 seconds with the two combined techniques. Let's look at the max-set evaluation benchmarks of 2019. We implemented the technique to simulate different encodings. For example, the encoding of QMaxset 2017, here the green lines without and with the techniques. Pacose in the 2019 variant without and with the techniques, and Pacose in the 2020 variant without and with the techniques. QMaxset in the 2018 version, which participated in 2019 max-set evaluation, there were only velocity gains and not that directly visible here. So I didn't show the solver here. Compared with the max-set evaluation benchmarks, here is Pacose and QMaxset 18, Pacose 19, QMaxset 18. QMaxset 18 in our environment simulated, and Pacose 19 in our environment with TrimMaxset and GBMO. But I want you to focus here on the two right curves. The old top solver combination and the new top solver combination. What is the top solver combination? These are n solvers run subsequently with a timeout of 3,600 divided by n each. The old top solver combination at first used UWR maxset for the first 1,200 seconds, then 1,200 seconds MaxHS, and then QMaxset 18. This was the best combination of any number of solvers run subsequently with the same timeout as the max-set evaluation if we use instead, after UWR maxat here, if we use then Percosa with the Trumaxat and GBMO, we are here at this line. And then as third solver, we use MaxHS. Then we improved the top solver combination by 13 additional instances. This is different than the virtual best solver, which solved here on our environment, on our cluster, 456 instances, and this new top combination is only 20 instances away from the virtual best solver. Okay, to conclude this talk, I talked about the new RSN application benchmark set with large instances, which was handed in for the 2020 maxat evaluation. I introduced two new pre-processing techniques, the generalized Boolean multi-level optimization and trimming the maxat instance. And I showed with experimental results that we could outperform all evaluation solvers by the application benchmarks. And we improved the top solver combination for the maxat evaluation 2019 benchmarks. Thank you for your attention, and yeah, I'm happy to answer your questions.
Great, thank you very much. So, are there any questions, please? I could start with something. So if you wanted to construct a scenario in which the pre-processing techniques don't pay off, what would it be? So when is an example not going to perform better?
So I cannot use generalized Boolean multi-level optimization for all instances. There are only around 25% of all instances in 2017, 18, 19, which are splittable at all. So when this is not applicable, yeah, then it's less efficient. Trimming the maxat instance turned out to be quite efficient for the new benchmark set. And for the maxat evaluation, we had improvements in timing and 2 to 3 instances additionally solved. Not that, yeah, it's hard to say how the instance would look. Probably only very, very few soft clauses.
Okay, thanks. Are there any other questions?
Quick question, it's a more general one. These maxat instances, the big ones, it seemed from what you indicated, they come from problems that can be illustrated as planar graphs. And I guess the variables would be communication variables, or, you know, in this, you know, so the constraints on them, you know, the clauses on them. Have you or anybody looked at the you know, analyzed the tree width of these clauses and somehow exploit this, you know, if it's you know, what is the tree width of these things? You know, it's like the, you know, so yeah, you know what I mean, I guess. And exploit that recursive structure that will arrive from a tree width decomposition. And this is the first question. The second question is whether the trimming maxat instance can be thought of as a branch and bound optimization. That was the two questions I would have.
Okay, it sounds like an interesting approach to look at the tree width or about the. Yeah, we could look at it. I haven't done it till now, of the weight distributions like that. And the second question again, what was it?
Well, if you know, if you basically had a if the trimming maxat instance optimization, which was a way of making possible branch and bound sort of optimization. So basically, once you've made choices in the algorithm and you've solved it, then you know that you know, other branches will not have to be pursued because they cannot beat the present best candidate set or candidate solution.
Might need to be a fairly swift answer if you can.
I don't know exactly. Sorry.
Thank you.
Okay, great. Thank you very much for the talk. And the last talk in the session is by Quang Lok Lei.
Yes, I'm here.
Great. Thank you very much. So please go ahead.
Okay. Okay. Please unshare your screen first. Okay. Yeah, I need to share my screen. Okay. Okay. Can you see my screen?
Yes.
Okay. Thank you very much. Okay. So hello, I'm Quang Lok. So I'm going to talk about a SAT solver in separation logic. First, I talk about the motivation. So an application of a SAT solver can be used in verification. For example, we look into the programs here with the main function. Okay, we have two parameters, x and y. Both of them are list, a single list, where the length is an odd number. So the main function, they will get the size of the list x and the size of list y. And as line number 6 here, it checks whether their sums an odd number. If this constraint holds, so an error will happen. So can we construct the verification condition to check whether the error happened or not? Okay, one approach for the verification is using separation logic. We can define a list with odd number, the length odd number is by the predicate odd. Okay, there are two parameters, x and n. S is the pointer and n is the size on the length of the list. So as the definition, S will point to a node, and the content of the node point to an even node. For the even node, it has two cases defined by two cases. In the base case, S point to null, and the size equal to 0. That means the heap is empty. For a recursive case, S point to a node, and the content of the node point to another odd list. Okay, that means the odd count to even and even count to odd, they are mutually dependent. And the VC, the verification condition, we can constrain the error position. The constraint to list to the error is S point to an odd list with the size M, Y point to the odd list with the size N, and we check whether the sum is an odd number or not. If VC is unsuch, we can conclude that the program is safe. Okay, so we need a SAT solver to check whether VC is unsuch or not. So our approach for a SAT solver for separate logic and inductive definition based on composition. So our work is inspired by compositional shape analysis. So in the analysis result of a program is defined in the term of the analysis result of its parts. So in the programs, the parts here, usually people use functions. So, and the analysis results is a summary of the function. So that means a specification in the form of precondition and postcondition. And to compute the summaries of the programs, we need to build a code graph of the programs. And we compute the summary of the functions in the bottom-up manner. That means the summaries of a function in the leaf of the graph will be computed first, and we move up until we see the root of the graph on the tree. And the summaries of programs is computed from the summaries of the code list. So in our analogy, a compositional SAT solver, so the SAT result is of a formula is defined in terms of the SAT result of the parts. So the parts here, our parts here is the predicate. That means we view the predicate similar to the function in programs, and the analysis, the satisfied result here we call that a base. The base is a formula without any inductive predicates, and it precisely characterizes the satisfiability of the formula. And the last one, the satisfiability of the basis is decidable. So now, given a formula, if we want to compute the base of the formula, we also could build a graph. Okay, the predicate graph, so odd count to even count to odd. Okay, and we need to compute the base of all inductive predicate inside the formula. After that, we use the base of predicate to compute the base of the formula. So we go up into the decision procedure. Our decision procedure. First, we need to compute the base of the formula. Second, we transform the base into SMT formulas. And the last one, we extract the SMT formulas using existing solver like CPC4 or YET3. So we come back to our example before, how we extract VC here. The first step, we compute the base of the inductive predicates. So here we compute, our system compute the base for the predicate. Let's say that S always point to a knot, and the size of the list is an odd number. The second, to compute the base of VC, we replace the base of inductive predicates into VC for the SM and the YM, and we obtain the VC prime. That is the base of VC. Okay, that's it. We replace for the SM here, we get here, and YM here. And the next step, we need to transform VC prime into SMT formula. So that's we transform the heap formula into the first order log formula. So for here, for example, S point to a knot, we transform to S not equal to none. And Y point to a knot, we transform Y not equal to none. And we transform the separating here between S and Y here by the constraint S not equal to Y. So at the end, we have a SMT formula pi here. And we use for an SMT solver to extract. And the underlying constraints here in pi here contradict. So pi is unsat. And because pi is equisat with VC prime also unsat. And VC prime equisat to VC, so VC also unsat. So at the end, we can conclude that the program is safe. Okay, so next we will give some intuition how we compute the base of inductive predicate. So we base on the method of infinite descent. That method actually to show application of method. That method show an equation P has a solution. So to do that, first we need to guess a simpler equation Q, and we need to show that the P and Q has the same solution, has a solution with some constant A. Next, we assume that P and Q hold for some natural number N. And based on that assumption, we need to show that P and Q both hold for another natural number M, such that M less than N. So if we can prove that, we can conclude that P has the same set of solutions with Q. And because Q is very simple, we can know the solution, the set of solution. So in our analogy, P here is the inductive predicate, and Q here is the base we need to infer. And in the paper, we propose a procedure to infer the base automatically, the base Qs automatically. So a bit more detail. So to infer the base for inductive predicates P here, we need to construct, we starting from the root, the inductive predicate, we unfold it, and we construct the regular unfolding tree. So we unfold doesn't mean we replace the predicates by the definition. So if we come to a knot for delta true here, inside delta true, don't have any inductive predicates, we can stop there. Or we meet one delta tree so that it is unsatisfied, so we can stop. Or we meet another knot for some bug here, we can make some back link. Somehow, you can read in the paper, somehow we can link back to some internal knot here. Okay, we can stop. And we call that the box here is the box and an internal knot is the component. So if the algorithm can stop, can terminate, we move to the next step. We will infer the base for all the subtrees with the cycle. For example, the subtree rooted by com here, we find the base using the method of infinite descent. Okay, for example, if we can find a base com That's in the base of the whole the subtree here. And in the tree, we do it bottom up, and in the tree until in the tree don't have any cycle. So at that time, the base of the root is a disjunction of the base on the leaf. Okay. So, and when we construct a regular unfolding tree on the cycle, we must satisfy the condition between the component and box must exist at least one unfolding of some predicate percentage, in this case predicate P. Okay, so and when we infer the base for the subtree here, we need to prove two things. In the first case, base we infer and delta 4, that's the base case here, both such when P has some unfolding as a constant A inside delta 4. And the second, we can assume that the base we infer and both such when P has some unfolding n time inside the box. And after that, we need to prove that base and com both such when B unfolded m times, when m less than n. And because of we need to satisfy the sound condition. The sound condition here have us prove the m less than n here. That is the condition for well-foundedness. Okay.
To be wrapping up in a minute or so.
Okay, so with just 1 minute. And we implemented the system in OCaml. Okay, do some experiments. And here we saw that the experiment without composition. So we run some verification program in some programs for with single list, double list, and collect more than 4,000 queries. And we run the query in two settings, with and without. You can see that, and we collect all the invocation history here. And at the end, we say the cost of with composition only less than 1% compared to without composition. And in the paper, we also show the correctness and decidable fragment. We show that on the existing decidable fragment, we can do composition. And we show some new decidable fragment and more experience to compare our implementation with state of the art solver in SLCom. So I'm going to conclude my talk about composition solver, and it's based on the base, and the base computed by the regular unfolding tree. Thank you very much for your attention. So I would like to answer your question. Thank you.
Thank you for the talk.
Okay.
Are there any questions, please? So I would ask a question about the technique. So yes. when you construct your formula that you check, it seems you manage with a single non-aliasing constraint in the formula, even though you're dealing with, I guess, predicates that in general could overlap further down in a sense in the heap. So could you give some intuition as to why that is? So, or is that not the case? Maybe in more complicated examples, it's different.
Yeah. So your question is about the arithmetic, right?
So when you generate an equisatisfiable constraint for predicates that are unbounded in depth, then how do you avoid kind of enumerating all the pairs of non-aliasing conditions that you would need?
Yeah, actually in the decidable fragment, we cannot handle the non-linear one. And also for the infinite one. So for the, I should emphasize that the procedure only works when we can construct the regular unfolding tree. And it's not always the case we can construct the regular unfolding tree in infinite time. So only in decidable fragment we can construct such kind of formula, equisat formula. So that's not always the case.
I see.
Yeah.
Okay, thank you.
Okay.
Are there any other questions?
I have a question. Can you comment on the decidable fragments? Can you characterize it? How does it relate to the bounded tree width fragments?
Yeah, the bounded tree, because the bounded tree fragments is the bounded tree fragments is only for the shape and not the numeric one.
Yeah, so actually we can ignore the arithmetic constraints for now.
Second, I just want to talk about the bounded Dutch fragment. Also, they focus on the entailment problem, and our work is such problem. And if we don't care about if we remove the every method, our fragment is more expressive than the bounded one. So we don't need for the shape only. We don't need any condition. So the desirable fragment for the such problem, we don't have any condition. Any shape is in the desirable fragment. But that's I want to emphasize that's in the such problem. And the bounded actually they focus on the entailment problem. So the entailment problem more, I think it's more complicated that compared to the such problem. That's why they had to bound the desirable fragment. Is this okay? My answer is okay. Yeah.
I think you're muted, Alex.
Ah, thank you. I hadn't realized. Yeah, so that's the end of the session. Thank you all for coming. Thank you again to the speakers.
Okay.
And enjoy your evenings or days, depending on the time zones you're in.
Okay.
Well, thank you all. And thank you also the session chairs. And this is actually the end of VMCAI 2021. So it's been a historic event. We've done this for the first time entirely virtually. In some sense, maybe hopefully also the last time, at least the occasion or the cause for that could go away. What I want to say is, like, please take part in the poll on our Clouder room, what to do in the future. And I'd like to say right away, I mean, as one of the three co-chairs, is that since I've spoken a lot here, I just want to emphasize that Sharon and Yakir, who are there, have done an enormous amount of work. I mean, Sharon gets up at who knows when in the West Coast with 4 children, and Yakir actually got a new baby last weekend. So I mean, this has been quite. I don't know how you do it. So I think if I may ask, please let them have an applause for actually doing an enormous amount of work, which I can certainly attest to. So, and yeah.
Thank you. I'd also like to thank everyone, the presenters, the session chairs, the PC members. Thank you very much for all the help. So yeah, I hope we finally got it. But I think we finally got a really nice program, and I'm very happy with the result. So thanks, and of course, thank you, Fritz, as well, for managing all the, especially making the Zoom and the YouTube channels work and all of that. So thank you very much.
My pleasure. So we've had a great VMCAI. There will be a VMCAI 2022. Watch out for announcements. If you have feedback, please do contact the steering committee or us. We'll be happy to take it up, and that's going to be maybe an opportunity to have more feedback this time than the previous ones, because it's the first time we've had this format. Andreas is here. He's a steering committee member, so he'll also be very interested to think about the future and hear about what we as a community actually can do in this setting. You want to say something, Andreas, or?
Well, nobody thanked you, Fritz. So let me thank you. And let me thank again all 3 PC chairs and the PC and everybody who participated. Thanks to you all.
Thank you all.
Thank you. Thank you.
And I have a last plug. So please go on over to Welcome to Copenhagen. There's a breakout room, and it's going to be a welcome to Copenhagen, because as you will find out in that session, Popl, which starts tomorrow, and think about the date. It's a very important date tomorrow. It's the first day of Popl. That's what's important about it. It's the 20th of January, 2021. Will be held in Copenhagen. If you don't believe that, come on over and watch for yourself. Okay. See you all.
Okay.
Thank you, everyone.